Participants are in the test,
Okay.
please come closer and occupy the front seats. Thank you.
Well, good morning, everybody. Welcome back. I hope you didn't have nightmares last night thinking about OJ electron spectroscopy and worrying about all kinds of aspects. So we're going to continue on with OJ spectroscopy. And some of you asked me about getting color copies of my course. And I just uploaded that copy in case you would like that. And on the first page of the notes is my web address. And I just added the notes. So if you go back to the first page of the notes, it has my web address, surfaceanalysis.org. Then if you use a / and then Pakistan with capital P, Pakistan, and then .pdf. So pakistan.pdf, you will access the notes in PDF form. So if you'd like those, you're welcome to use those notes, okay, as well. Okay, so I just did that at a request of some of you. So this is where we finished yesterday, talking about spatial resolution and so forth. And I was asked last night after the course about how you do the quantitative analysis in mapping. Well, that's exactly where we're going to go next. And so this is the way that we do a quantitative analysis for mapping, scanning OJ maps. And this corrects to a large extent for both topography and backscattering. So I mentioned yesterday that we do mapping in the direct mode. This is the part of an OJ spectrum here. Imagine this is an OJ peak, and there's a certain background associated with the peak. And in mapping, what we do is we measure the peak height above background. And there are different ways this has been done over the years. The simple way is just to measure the peak height minus a background value over here. And this is something that you select. It's subjective. And one of my colleagues, I mentioned yesterday also, that Martin Prutton is the world expert in OJ mapping. And what he did, he proposed to extrapolate the background underneath the peak and measure this background. So this is a better value of the background. So this is designated here as NL. So it's an extension of the background. And this can be done very easily in the equipment because the instruments typically have a way of measuring 2 points or 3 points to determine the OJ intensity in this direct mode. And on the right-hand side here, he has plotted different ways of measuring the signal intensity. And he found out that the best way was to subtract this count here, N1, from the extrapolated background, and then divide also by a background. So the reason it corrects for backscattering is because when you have backscattering, the OJ peak increases, but the background increases as well, proportionally. So by dividing the background into the OJ peak intensity, we correct for this backscattering. So in the imaging, that's what we do. And this is a very impressive study that he did. He took a sample. This is a silicon sample with polyhedra, and he coated it with gold. And you can see over here, just taking the peak minus the background, which is what people used to do, you get big changes in the intensity of the gold signal in the direct spectrum. And this illustrates how many pixels have different intensities. So you have this region here in red with high intensity, and over here in blue with low intensity. And this is on the flat part of the silicon, and this is on the sloping sides that he formed by etching the silicon. So he had these mesas, these top flat regions, and these sloping sides on the crystal. and a large change in intensity. And then the same sample, by taking the intensity of the peak minus the extrapolated background and divided by the extrapolated background value, you can see now that this is sharpened up. The intensity of variation is much smaller, and the effects of the edges you can see here on the right-hand side. But the variation intensity has been reduced drastically. So this is what's been recommended for doing mapping in Auger spectroscopy. The peak minus the background divided by the background, and ideally the extrapolated background. And also, in looking at samples, we talked about the backscattering, how it affects the analysis. And this is a nice example that I like to take to show you about backscattering. And these are calculations, again, we call these Monte Carlo calculations. This is a titanium nitride cube on steel. So this is a titanium nitride cube here. You can see it better here on the right. So this is titanium nitride, and this is a steel holder on which the titanium nitride cube is mounted. If you use a high energy electron beam, 20,000 electron volt beam, this is the beam diameter, and use Monte Carlo calculations, you can see that the electrons scatter out of this cube. So they still have significant energy, and they are going to produce Auger electrons on these surfaces here of the steel. If you reduce the beam energy down to 3,000 electron volts, the beam becomes broader, but now the Monte Carlo calculations show you that typically all the scattering is going to occur in the cube, and you wouldn't expect to get significant signal from the iron walls. So this is a nice example of what you would expect to get on such a sample. And here are the Auger results from that particular sample. This is the titanium nitride cube. And up the top here, you can see that the electrons have scattered out of the cube. So besides seeing peaks over here for titanium and nitrogen, you'll also see significant peaks from oxygen and iron, as well as carbon here. So these signals are coming from the walls of the holder, not from the sample. And dropping the energy down to 3,000 electron volts, you now see that the signal is coming essentially from titanium nitride. Oxygen is much, much smaller, as is carbon, and iron is not really detected. So this is very important in Auger spectroscopy to remember. I said yesterday, an electron beam can be made a very small beam diameter, that the Auger signal does not come just from where the electron beam is impacting the sample, because the backscattering can occur and you'll get Auger electrons produced from regions nearby. The lower the beam energy, the more accurate that's going to be. The higher the beam energy, the more backscattering you're going to have, and then you're going to have signal from the surrounding regions. So you must be very careful in interpreting your results. And of course, you can always change the beam energy to see the effect of scattering on your spectrum, to know that you're getting signal from nearby, as well as on the point where the electron beam is impacting the sample. And here's a line scan. I mentioned yesterday, I like to do line scans as opposed to mapping typically, because it's much faster. So this is the same sample, it's titanium nitride cube here, 0.7 micrometers size, and on steel, 20 kV and 3 kV. And this is a scan across the sample. And this is the iron holder. Then you got this valley. Then you've got the titanium nitride, and then back down to a valley. And you can see here when the electron beam scans across the center here, the iron signal, that's the one here on the top, only decreases by about 50% and goes back up again. And we know there's no iron in this titanium nitride. So this iron signal is coming from the the backscattering, the electrons coming out of that cube and striking the walls and giving us an ion signal. On the right-hand side, using the low beam energy and scanning again across the center, now you can see that the ion signal drops off down here almost to zero. We don't have any significant backscattering into the surroundings. And also you can see the lower intensities of the carbon. So this is important to remember about the backscattering. And this also arises when we're doing analyses. And I want to show you a few comparisons between Auger electron spectroscopy and energy dispersive spectroscopy. So we can look at the Auger electrons coming out, and maybe we can look at the X-rays coming out and compare them. And some Auger instruments have EDS attachments on them as well. So you can do both these kinds of analyses. Now remember, the Auger electrons come from near the surface, and the X-rays can come out from that particular inverted balloon we talked about yesterday. So we have these different regions from which the signal is going to come. On the left-hand side here is the SEM image of our sample. And this is copper. This is a copper plate on a tantalum film, which is on silicon. So if we do the analysis here on the copper plate, on the Auger result, you can see the peaks here labeled as copper. These peaks copper. And these peaks up here are labeled tantalum. And there is no detected peak from the silicon substrate, just from the copper flake and the tantalum film. And silicon would appear here, but there's no signal there. Also, you can see some peaks here from the contaminants of sulfur, carbon, and oxygen. The X-ray analysis in EDS, you see enormous peaks from silicon, and you see also these peaks here from the tantalum. So this is looking more into the bulk of the material. So the electron beam is penetrating into the sample, and now we can get the X-rays coming from deeper in the material. And copper can be detected here, and you can see the small peak here from copper in the EDS. So again, Auger spectroscopy and EDS give you different depths of information. I had a colleague come once, and he was growing a film on fibers, and he had used SEM for analysis and was doing EDS. And he came to me and said, "I can't see my film. All I see is the fiber." And he asked me if I could use Auger spectroscopy to see if I could see the film. Did he have a film on the fiber or not? He could not tell. And when he gave me the fibers and I looked at the fibers, I only saw the film and I did not see the fiber. Because of the Auger spectroscopy, the depth of analysis was just on that film he put on. So the two techniques are very complementary. Okay, the Auger spectroscopy is looking at the top several layers, and the EDS is looking down the depths of 1 to 3 micrometers approximately. So he was very happy that I could detect his film. So if you're growing films on materials or coatings, and you're trying to protect something, it might be a corrosion protection, it might be decorative, anything like that on a film that you're growing, and you can't detect it in your X-ray machine by EDS, Auger spectroscopy is the answer, or one of the surface techniques is the answer to see if that film's there. So they're both very, very useful techniques if you're growing films or coatings. So you might be growing a coating to protect against wear, something like that on a material. Now here's another example in the semiconductor industry. In the semiconductor industry, we're often interested in looking at defects on the surface of silicon. What are they? Where do they come from? So again, using an SEM, looking with electron dispersive spectroscopy, EDS, looking at the X-rays coming out, here's an example of what you see. So in the SEM, you can see this defect, and you'd like to know what this defect is. And this is part of the device here that you can see. Okay. So here's our defect, and putting the electron beam on the defect. Here's the EDS spectrum. So you can see this is on a silicon wafer. So we have silicon, and looking at the defect. And off the defect, this is the EDS spectrum, and you can see the peak from silicon, and you can also see this peak from carbon. And on the defect, what's the difference? Well, you can see the presence of oxygen. So based on the EDS analysis, you might interpret this then that the particle is a silicon dioxide particle, or some kind of a silicon oxide particle on your wafer. See? So this is something that you would maybe think that you have. But again, remember that you're looking down deeper into the material. So if you look at the same sample with Auger spectroscopy, do you get that same answer? Do you find silicon dioxide or not? So when you do an Auger analysis, here's that defect that we're talking about. And here's the background. And this is the spectrum from silicon. This is a low energy Auger spectrum of silicon here. It's around 92 electron volts. And up here is the high energy spectrum of silicon. You have a low energy peak and a high energy peak in the case of silicon. When we put our electron beam on the defect, and the defect is small, 0.2 micrometers, this is the spectrum that we get. And now you can see that we also have peaks from titanium. So it turns out that this particle is not silicon oxide particle, but it's a titanium oxide particle. See, so it's very different from the EDS. So for defect analysis, things like that, Auger spectroscopy is really needed. And this is one of the main areas of Auger spectroscopy today. Apart from metallurgy, looking at metals, is also the semiconductor industry for identifying particles and so forth on wafers. And on the right-hand side, I mean, you've already solved the problem. You know what it is. It's a titanium oxide particle. But if you do mapping, then you can see over here the overlays of the different maps. Titanium is in green. That's this defect particle here. This elemental silicon is in red, and silicon nitride's in blue. And this can be obtained from the chemical shift of the high energy nitrogen peak. Sorry, the high energy silicon peak, to distinguish between the silicon element and the silicon nitride because of the chemical shift we talked about yesterday. So Auger spectroscopy, again, extremely useful in analytical needs. Now, a lot of you I've been talking to some of you, a lot of you working on nanoparticles. And nanoparticles is a very important area of research. And Auger spectroscopy is also used in analyzing lots of nanoparticles. And well, these are rather large compared to a lot of nanoparticles you might be working on. These are a couple of micrometers in diameter, these particles. And these are nickel particles. And they're on indium. So these are some maps that were taken. On the top left is a map. These are spheres of nickel. And you can see the nickel intensity here on the spheres. This is the SEM image. And over here is the indium. And you can see the complementary nature of these signals. So where this is bright, this is dark. So this is nickel and this is indium. And down here are also maps of oxygen and carbon. But in mapping, most of the Auger maps can be also misleading because these images are not giving you really a quantitative analysis of how much nickel you have or how much indium you have. So a lot of maps, the maps you're putting some kind of a level. If the signal is above a certain amount, you say it's present. And if it's below a certain amount, normally you say it's not present. And that's really very misleading. And that's another reason I do not like to do maps because of that. So line scans, again, are far superior to mapping and are much quicker. So maps take a long time, they look nice, and they help sell instruments. And the manufacturer of this instrument, Physical Electronics, uses this kind of a slide to try to sell you their instrument versus other manufacturers. Because of this, their cylindrical mirror analyzer reduces shadowing effects. And it's really misleading. So if you take a line scan across one of these spheres, what do you see? You see what's really happening. So you're saving a lot of time, but you're also getting an idea of a quantitative analysis as well. So here's a line scan across one of the spheres. The electron beam is scanning where this white line is. And here are the signals. So it's a nickel sphere. So the nickel signal here is in red. And you can see it's flat here. It's essentially the zero level. And then it rises as the electron beam goes onto the nickel. And as it goes across the nickel sphere, there's some little variation in the signal. And that could be from contamination on the sphere. And over here again, the nickel signal drops off down to zero because we're off the nickel sphere. But look what happens to the indium signal. Remember, this is the background, indium. So here's the indium signal. There's a little drop here, and there's a carbon particle here that's increased intensity, and the indium comes. Now, when you're on the sphere, look what happens. You still see an indium signal. And the indium signal is not going down to zero until you're basically in the center of this few micrometer diameter sphere. And then as you come across the other side, you start to see the indium again, even though the beam is not on the indium, it's still just on the sphere. And that's because of scattering. So the electron beam is scattering out of the nickel sphere and striking the indium and giving you a signal from the nearby indium. So the line scans are much more informative than the maps. The maps look nice, but they don't give you the information that you really would like to have. And the line scans, therefore, are far superior and much faster. And you can make several line scans at a much quicker time. Okay, but line scans don't sell instruments. Okay, this line scan is not going to sell the instrument as easily as the other one I showed you with the mapping. But I prefer line scans or multiple point analysis, where you do multiple points here on the indium and multiple points on the sphere. So if you're looking at spherical particles, remember that the electron beam using Auger spectroscopy is going to scatter outside your particle and give you signals from nearby. So this is where you want to use a low beam energy if possible, as long as it's compatible with your nanoparticle size to reduce backscattering and get you more information about the particle itself. And again, you can change the beam energy to see how much scattering you're getting at different beam energies to help understand what the particle is and what's nearby. So this is extremely important to realize in studying nanoparticles, because Auger spectroscopy is often used for nanoparticles because we can look at very small areas. Another important application in Auger spectroscopy is segregation of elements. So you might have a material, and this is an example of segregation of tin in a steel. So we have a steel sample, and on the top left, is the SEM image showing you the grain structure on the steel surface. And you're heating it. Now, Auger instruments often have a thermal stage where you can heat the sample in situ. So you don't have to move the sample, take it outside, heat it, put it back in. So you can heat it in situ. And as you heat it, you can examine the composition at different grains or take maps across part of the surface. And, oops, sorry. So here you can see these grains. This is a 200 micrometer marker here on this image. And here you can see the tin. This is a tin image after heating to 700 Celsius. And you can see on some grains, you have higher concentration of tin than on other grains. And over here on the right-hand side, it shows you the tin Auger spectra in the direct mode. So this is before heating. Then here's with time. With heating, you can see the tin signal growing on a particular grain. So you can study these thermal segregation on the steel. And down here is the atomic concentration. Starting off at 0, this is 0, and this is about 5 atomic percent of the tin. So Auger spectroscopy is also excellent for studying segregation, and you can also examine the different grains. Another example of growing films. This is a chemical vapor deposition, trying to grow a film of carbon, boron, nitride. And in looking at the SEM image here on the left-hand side, this is a bar marker here, 50 micrometers. You can see it's not uniform. So you don't have uniform growth. You'd like a uniform film. So looking at SEM, for example, you could see, same as this in the Auger instrument, you can see the growth is not uniform. So it's nice to know what is happening. So you want to see carbon, you want to see boron, and you want to see nitrogen in our film, but something's happened. So here on the right-hand side is a map showing you carbon in red and boron in green. So you can see these darker regions here, these islands are going to be boron rich. Okay, boron's higher here than this region. So you can see the film is not uniform, and you can see what's happening, what the compositions are. But again, I like to do point analyses. I would prefer to do point analyses in several places here, and also on several of these different particles, islands here that are grown. And here's an example of 2 point analyses. Number 1 here on one of the islands that have grown, and number 2 here on the background. So you can compare the actual compositions. The map just shows you one is higher than the other in different places. It's not really quantitative. And these are the Auger spectra, which are going to be more quantitative and give you better information. So you can see that these islands, there's the Auger spectrum, you see the boron, and you see oxygen. But in the background, you see also some boron, small concentration, and on these parts, carbon, nitrogen, and also some oxygen. So you do have boron, carbon, and nitrogen in this film. And over here, this is really a high boron. But if you go back to the map, you see, you might think that this background region is just carbon, but there's still boron present. There's just a lower concentration than what it is on the particles. So the maps can be misleading because they don't really give you that quantitative information, whereas the point analysis does give you that information. So if you're growing films, and whether it's on a semiconductor, whether it's on metals, for whatever purpose, OJ spectroscopy can be extremely useful to help you understand your growth, the composition. So if you find different features in your SEM image, you can identify what's present at those different places and change the parameters for growth to try to get a more uniform film. So you have feedback. So you do a trial experiment, see what's growing, find out what you're getting, and change parameters so you can adjust the growth to try to get the growth that you want and uniform growth. So back and forth to get the end result. So that's what you want to do. You want to have analysis capability and to be able to improve your growth mechanisms. Now I'm going to turn to quantitative analysis. And I mentioned this is going to be more difficult because of backscattering. And quantitative analysis in OJ electron spectroscopy uses typically what we call sensitivity factors. So in the instruments, there are sets of intensities for each of the pure elements. So the intensities, the intensities have been measured from pure elemental standards. So you put different materials in your system and measure the intensities of your OJ peaks. So some elements are going to give you bigger peaks than others. And that gives you what we call the sensitivity factors. If you get a large OJ peak from a certain element, that means it has a large sensitivity factor. If you get a relatively small peak from the pure material, it has what we call a small sensitivity factor. So if you're doing a quantitative analysis, you have to correct for that fact that some elements give you big peaks, other elements give you small peaks. So by dividing your measured signal, okay, this is the signal you get from your element A, the measured element A, and this is the intensity you get from your standard of that element. This one here with the infinity sign. So this normalizes it. This corrects somewhat for that, set by the sensitivity factor, corrects for how sensitive that element is in OJ spectroscopy. So dividing what you measure by what you get from the pure element gives you an idea of the fractional amount of that element. So that's what we do. We measure an OJ intensity and we divide by the OJ intensity from that pure element to give us the relative concentration. And we select one peak for each element. And in practice, what we do, we divide that measurement by the sum of all the measurements from the different elements. So when we add up all the X's, we'll get 1. And if you multiply by 100, you'll get percentage concentrations. So this is just a normalization factor here by summing up all of these values for each element. So this is element A. And by taking each element into consideration, you get the fractional concentration of each of the elements. And that's how we do the quantitative analysis in OJ spectroscopy. And as I mentioned, it's always done for OJ scans in the derivative mode. Now, the OJ intensities are really peak areas. They're really, you should be measuring the peak area in that so-called direct spectrum. But that's not easy to do. So that's why people typically take derivatives and peak-to-peak heights in the derivative spectra are what are used for quantitative analysis and also in sputtered depth profiling. We take the derivatives of the direct spectra and measure those peak-to-peak heights of the OJ features in the spectrum and divide by the sensitivity factor for that same peak from the pure material to do our quantitative analysis. Here's just a graph of relative sensitivity factors. This is from physical electronics. It's using peak-to-peak heights in the derivative spectrum. These are values using a 5,000 electron volt beam, and these are measured relative to silver, being given a value of 1 using a 3 keV beam. So what you do is have a material like silver, which gives you a big signal in Auger spectroscopy. It's easy to clean silver by sputtering it, and it stays clean for a significant time. And you compare then the other elements with silver. So everything's compared with silver, and that makes a correction for difference might be in beam current and things like that. So we often talk about relative sensitivity factors, and they're measured relative to another element, and most often silver. But the important point here I want to make is that these sensitivity factors, how big the peak is from the pure element, varies a lot between the different elements. So this is a sensitivity factor compared to silver, and silver's number 47. But remember I said it's a 3 keV. This is 5 keV. So the silver sensitivity factor is not quite 1 compared to the 3 keV beam, but it's close to 1. And this is logarithmic. This is atomic number. And you can see that the sensitivity factor varies by a factor of over 100 between the different elements across the periodic table. So this means you must be very careful. And because a peak is big compared to another peak in a spectrum, doesn't mean to say you have more of that element. Because silver gives you a large peak, whereas some other elements give you small peaks. So you could easily have a difference in concentration of 10, even though the peak intensities may be the same. The peak-to-peak heights might be equal. The relative sensitivity factor must be used to correct for that fact that some elements give you big peaks and some elements give you small peaks. And that's that relative sensitivity factor. And the manufacturers provide these kinds of numbers in the instrument when they supply the instrument to you. Unfortunately, from my experience, the relative sensitivity factors supplied by the manufacturers are typically not very good, unfortunately. And the results can be off by much more than a factor of 2. And if you really want to do accurate quantitative analysis, you must really measure standards in your own system that are close to the compositions that you're measuring. So if you're looking at silicon nitrides or silicon carbides, you would like to have pure materials in your system and measure your own relative sensitivity factors. And you'll get much better results than using these generic values that have been put into the databases in the instruments. So the quantitative analysis in Auger spectroscopy is not that good. We can definitely compare samples. You can see that the peak of a certain element is bigger in one case compared to another case. You'll know you have more of that element than in the other case, but the accurate quantitative analysis, the absolute concentrations are not necessarily accurate. So the sensitivity factors, if you want to do accurate quantitative analysis, the sensitivity factors should be measured in the same analysis system that you're using and with the same analyzer resolution that you're using, because some instruments allow you to change the resolution of your electron energy analyzer. And the composition of the reference material should be as close as possible to that of the unknown. And as I mentioned, the sensitivity factors from the pure elements are most commonly used, but they can produce significant errors in concentration if we neglect these so-called matrix effects. And matrix effects include the backscattering, for example. and density and things like that. So when you change the matrix in which a certain element is present, it changes the backscattering, it changes the inelastic mean free path. So it's going to change the quantitative analysis. In this slide, I show you what are called standard Auger spectra, copper, silver, and gold. So these are reference spectra that can be used to calibrate your instrument to ideally give you better sensitivity factors. So these were established by workers at the National Physical Lab in the United Kingdom. And these are spectra of copper, silver, and gold. And these have been offset by factors of 10 and 100 here at logarithmic scale. And this is kinetic energy, also on a logarithmic scale. But it shows you the Auger spectrum that you get from these copper, silver, and gold samples, basically with everything removed. They removed the fact of the backscattering, they removed the effect of the analyzer, the effects of the detector, and so forth, and came up with these, what they call the standard Auger spectra. So these are reference spectra that were published in 1990. So more than 30 years ago, we have these reference spectra. And unfortunately, the manufacturers never adopted this, and they should have adopted them. These reference spectra should be included in all Auger instruments. And you should have access to these standard spectra. So you can check your instrument and then see how it's performing. And unfortunately, this is not done. And this is one of my disappointments in Auger spectroscopy, that the manufacturers never did this. They never put these spectra into their instruments to calibrate their instruments. And if they did, we would get much better quantitative analysis, particularly between instruments. But you still have to correct, of course, for backscattering and things like that as well. But you'll be able to study the spectra much more closely. So if you took a spectrum of a sample in one instrument, and then you took a spectrum of that same sample in a different instrument, maybe made by a different manufacturer, the spectrum may look different. And that's because of how that different manufacturer's instrument's working. They won't give you the same looking spectra exactly, but if you calibrated your instrument by looking at the standard spectra, you could normalize them. So you could compare one instrument with another exactly, and you know how one instrument performs compared to another exactly. And this is something that really should have been done. I think a little bit of this is politics, and was never adopted because of that, I think, between different countries, unfortunately. Now, in the Auger instruments, you can do a quantitative analysis, but again, you're using the sensitivity factors that come with that instrument. And you can change those sensitivity factors if you have your own measured sensitivity factors. But if you use the default sensitivity factors, you will get a quantitative analysis. But as I said, it may not be very accurate. And one way to check quantitative analysis would be to put in known samples and see how accurate the quantitative analysis is. So here's an Auger spectrum, and it's in the derivative mode. And as I mentioned, that's what we use for quantitative analysis. And you can see peaks here from silicon, high energy peak of silicon, a smaller high energy peak of silicon, and down here we also have low energy peaks of silicon. Now the low energy peaks involve the valence band, and these peaks are going to change their line shapes when we change chemistry. So these are not going to be good to be used for quantitative analysis because the line shapes are different. So if the line shapes are different, the derivatives are going to be different and will not be useful for quantitative analysis. So you'd want to use these high energy peaks. Oxygen, a large peak, a smaller peak, carbon. You remember yesterday I talked about the carbon line shapes. This carbon line shape is very typical for one of the line shapes. Remember what this one is? It's not silicon carbide. This is that very asymmetrical peak that I showed you. If you go back and look at your notes, you'll see that in the carbon line shapes that I showed you, this carbon line shape is very typical for graphite, graphitic carbon, this very asymmetrical peak. So this is going to be a surface contaminant on a silicon oxide surface. And also in this spectrum here is a peak here from sulfur. And the quantitative analysis measures the peak-to-peak height of oxygen, compares it with the sensitivity factor from the table. Silicon, peak-to-peak height, compares it with the value from pure silicon, and so forth, and you get the concentration table here. And you can see that carbon is just over 50%. Oxygen is it's got 26.7 here. And again, it shows you that even though the peak of oxygen is bigger than carbon, the concentration of oxygen is about half of carbon. And that's because of the sensitivity factors for oxygen and carbon being very different. Silicon, about 20%, and the sulfur, about 0.4 atomic percent. So in Auger spectroscopy, we can typically measure concentrations down to about 0.1 atomic percent. It depends on the sensitivity factor for that element, but that's a typical limit, about 0.1% atomic. And I mentioned yesterday in the same figure that I showed you, the software did not identify these peaks here, okay, in the spectrum, which are copper peaks. So you would have to put those in to manually. The software did not identify these, so you'd have to add these manually to include the copper concentrations in your quantitative analysis. Sorry, well, the sample, sorry, of the iron, too low energy there, the iron peaks, sorry, my mistake. And so here is where you put them in manually. You've got these 3 peaks here of iron, and the iron concentration is about 1.7 atomic percent. So these peaks here are iron, 3 peaks that you've got on the surface here of iron, and you have to put them in manually to include those in the quantitative analysis. And then you have questions, of course, with noise. Is this a peak here? Is this another element? Okay, or not? So you have to really include these kinds of things. And this is where the copper is actually. If you take the data for a longer time, there's actually some copper present also on this particular surface, but you can't detect it clearly in this particular scan because the signal to noise is not good enough. And if you suspect there might be other elements present, you can scan this region for a longer time to get better signal to noise so you can see that copper. So this is a copper, there's a little peak here that's really barely above the noise, and this is a copper peak. So you do have some copper present as well. Now, another thing to remember in Auger spectroscopy, with electron beam, we can also have damage in our analysis. Electron beam can damage the sample. And Auger spectroscopy can produce different kinds of damage. And this slide illustrates some of those, and this is taken from one of the chapters in our book about the beam effects during Auger and XPS analysis. So, for example, you can have desorption of particles or atoms from the surface. The electron beam can also provide energy to enhance absorption of background gases in the vacuum system onto the surface. It could also disorder the surface. You can have impurity segregation, where the electron beam is hitting, backed by localized heating. You can also create charge defects, bond breaking. You can have a certain species on the surface here to form the layer of certain species. An electron beam could break the bond, change the chemistry, and also perhaps dissolve some of the species. But lots of things can happen. And in polymer work, Auger electron spectroscopy is quite difficult because of the fact that the beam damage can be very significant in looking at polymers. People have used Auger spectroscopy to look at polymers, but most of the work on polymers is done using X-ray photoelectron spectroscopy or SIMS, not Auger spectroscopy, because of the significant damage you can get with a polymer. This is an example of electron beam effects and work I did a long time ago of carbon monoxide adsorbed on nickel. And in the top here are spectra from carbon and oxygen. And the line shape of carbon, this is typical for carbon monoxide that has not decomposed on the surface. And this is carbon line shape is also very different from what I showed you before for graphite or silicon carbide or metal carbides. So this is a fingerprint line shape for a carbon monoxide molecule that is absorbed on the surface of a metal. And when you leave the electron beam on for a certain time, you'll see the line shapes are changing. So this line shape of carbon is changing from this particular shape to this one, and finally to this one. This one is the line shape that I mentioned yesterday, which is typical for a carbide. Remember that I told about carbide is typically 3 fairly symmetrical peaks with an asymmetrical feature on the right-hand side. So the electron beam has changed the absorbed carbon monoxide molecule that you have on the surface to a metal carbide. So it's formed a nickel carbide from the electron beam. And if you want to compare how much carbon is present, I can't use a peak-to-peak height to compare the amount of carbon because the line shapes are very different. So what I have to do is go back to direct spectrum and measure the areas under the carbon peaks and compare the areas under the carbon peaks to see how much carbon is there. So some carbon has been dissolved from the surface and some has been changed into a carbide. So you must go back to direct spectra to measure the areas under the peaks to do a quantitative analysis that compare these concentrations of how much carbon there is. You can't do it from the derivative spectra because the peak shapes have changed. So when the peak shapes change, the quantitative analysis is not going to be accurate because a sharper peak gives you a big derivative. Okay, and a broader peak gives you a smaller derivative. This is a table. You may not be able to read it in the notes, but it gives you an idea of how electron beam damage changes with different materials. Some materials are quite stable and others are not. So in this particular table, the materials at the top are more stable than those further down on this list. And this comes from an appendix in our book about the electron beam damage. This table shows you. And it compares damage. These are from experiments that people have measured and recorded in the literature. This column shows you electron beam energy that was used. The beam energies are not the same. Okay, the beam energies are different. And of course, the damage will depend upon the beam energy and also the beam current. And as you can see here, for example, silicon nitride, okay, the stability versus other elements down here. As you go down, you see that you can get beam effects on the changes in composition with time. So here's one of the polymers, pan, other polymers down here and so forth, are very subject to beam damage. Okay. So this just gives you an idea of how stable they are. So this is the stability sort of table here, giving you a critical energy dose for damage, comparing them. This one's stable. This one has a number of 10, number of 1, and down here 0.01, and so forth. So these are not stable with the electron beam. Insulating samples can also be a problem in taking an Auger spectrum because of charging effects. We're using an electron beam to measure our spectrum. And if the sample charges, the electrons coming out of the sample, the Auger electrons, the backscattered electrons, all these electrons are going to change their energies. So if the sample charges up to be a negative potential, it's going to push the electrons away from the sample when they come out, and they'll go to higher kinetic energies in our spectrometer than what they should be. So here's an example of a sample that charged, and you can see here that there's no signal here at lower kinetic energies, and up here you can see some broad peaks here, carbon, oxygen, aluminum, which are not at the correct energies. So this is a sample I put in the instrument for this piece of sapphire for Mike Kelly, who wrote the chapter on insulators. And he did not have a spectrum of an insulator. So I just put a piece of sapphire in. I tried using a 10 keV beam, and I got this spectrum here showing you clearly that there's charging occurring. And in my case, all I did was change the beam energy from 10 to 5,000 eV, from 10,000 to 5,000. When I also go down to 5,000 electron volts, you can see now the peaks have shifted back to where they should be. And also the peaks are much sharper than what they were in the case where there's charging. So when charging occurs, the peaks are going to be the wrong energies. They're going to be broad. And changing the beam energy is one way to reduce charging, trial and error, or changing the angle of incidence by tilting your sample, something like that, to minimize charging. So when the sample charges, the peaks shift and they become broad. And in the top case, the peaks are shifted by about 200 electron volts from where they should be in the Auger spectrum. So if you're studying insulators, Auger spectroscopy is more of a problem, but there are ways to overcome the charging. And changing the beam energy is one way, and that's one I just showed you. Using a more glancing incidence beam on the sample is another way that you can do it. And sometimes by putting a coating on the sample and leaving a region here uncoated. So the electrons that are coming from the electron beam have a shorter distance to travel to go to ground and reduce charging. So there's just 3 ways that people have used over the years to reduce charging effects. Changing the beam energy is a common one. Changing the angle of incidence is also a common way, typically by tilting the sample or by putting some kind of a coating or even a mesh. Some people put an open mesh on the sample and then look between the holes in the mesh on their sample, and the mesh is grounded. So you have a shorter distance for the electrons to travel to get rid of charging. So these are just some of the ways to help reduce charging. A couple of examples. This is actually one that's sort of the opposite, increasing electron beam energy to get rid of charging. And these are the SEM images, 5, 10, and 20 keV. And when you have charging in the SEM, you'll often see this by some kind of a bad image or a very different intensity on the secondary electron image. And you can see that this sample here is charged significantly, and the Auger spectrum taken from this particular place is just got this one big peak here around 500 electron volts. So this is not going to produce an Auger spectrum for you. Changing to 10 keV, you can see the SEM image is improved. You can start to see features here on this part of the semiconductor device. And you can see the reduction also on this region around the outside. And now you can see that I can start to see features in the Auger spectrum. And going to 20 keV beam energy, you can now see the Auger peaks very clearly and identify what they are. Okay, so you can see a peak here from oxygen and a peak here from silicon in this particular case. So changing the beam energy again is a very useful way to get rid of the charging. Another example, here is the SE image here. This was on a read-write head, and you can see again a problem in analyzing this region here where the plus sign is. And by changing the angle, by tilting the sample, you get rid of charging. So here's the first Auger spectrum. Again, no signal, low kinetic energies. You get this large peak from charging, and then there happens to be a small peak here from the Auger electrons. But by changing the angle, by tilting the sample from an angle of 60 degrees to 80 degrees in relation to the surface, you now see a nice SE image, and you now get a nice Auger spectrum. So by changing the angle of incidence of the electron beam on the sample also is a way to really improve the charge control in your analysis. So those of you that are working on insulating materials, on semiconductors that charge up, changing different parameters, trial and error to get rid of charging. And from experience, if you're looking at similar samples from one day to another, you will know what method is best in your case to control charging. Another approach that's been used is to use a low energy ion beam, okay, in conjunction with your incident electron beam. So here's your electron beam coming in onto your insulating sample. And it's been found that using a low energy ion beam can also be quite effective in reducing charging on insulating sample. So you use a low energy ion beam. Now you must be careful, because if the ion beam is going to have the possibility of sputtering to remove material from the ions impacting the surface. So it must be a low energy ion beam to reduce the probability of sputtering away material. So the use of a low energy ion beam is been found to be quite effective also, looking at samples that charge. And a couple of manufacturers with Auger instruments use a low energy ion beam as well to control charging. But remember, the ion beam has to be low energy. And what do I mean by low energy? Again, trial and error. Some manufacturers use 100 EV for their ion beam. And in my opinion, that's a little high because you'll get some sputtering. But it depends on time, how long the ion beam's on. To me, low energy ion beam is more like 10 EV. The 10 EV ions can also produce sputtering, but it's going to be much smaller than 100 EV ions. So again, it's time. How much time you're going to leave, how much time you need to acquire your Auger spectrum to do your analysis. Here's an example of using a low energy ion beam in the semiconductor industry to reduce charging effects. So here's a part of a printed circuit board. So the printed circuit board is going to give us charging problems. And here on the left-hand side again is an Auger spectrum. This is using a 5,000 electron volt beam to take an Auger spectrum. And you can see it's essentially useless. It doesn't really tell us anything about the composition because of charging. And this is the part of the circuit board over here that's been studied. And by using an ion beam in conjunction with the electron beam, this is a case of using a 100 electron volt ion beam, you can see the charging's been removed. It's been eliminated. And now you can see these peaks, sharp peaks here from nickel, and also you can see peaks from gold. So the low energy ion beam can be also very effective. Data acquisition and taking our spectra, we have with modern machines. When I first started taking Auger data, we didn't have computers. My first spectrum was 1968. Our spectra on paper. Okay, today the instruments all have computers, and the computers are great because you can save the electron gun settings. If you change from a 5 keV beam to a 10 keV beam, the computer can keep the information about all your lens conditions. If you change your beam current, you can save conditions, so you can easily change from one particular energy or particular beam current to another one because that's saved. Okay, also for doing point analyses, doing line scans, much easier. The same with the analyzer you're using. You can select the energy range across which you want to take your spectrum. You can change the time for acquisition. All these can be changed and saved in your computer. And also for peak identification, we have the software, but it's not always accurate. Okay, for sputtering and depth profiling, we can sequentially turn on a sputter beam, turn it off, measure our spectrum, and do that many times to measure different depths into our sample. We can also move the sample around, or we can move the beam around over a certain region to look at different points on our sample. So when I started off, we didn't have these capabilities. As I said, it's all on paper. So if I wanted to measure an Auger peak intensity, I had to use a ruler. So all our spectra were taken on graph paper, and we could measure the heights using the intervals on the graph paper. If we wanted to measure the areas of a peak, particularly at XPS, which I'm going to talk about later, we had to measure the area under peak, and you could actually measure how many little squares you had on the graph paper under a peak after subtract the background. And we had a very nice mechanical tool. There's a mechanical tool called a planimeter. Has anybody here ever used a planimeter or knows what a planimeter is? Okay. Oh, you have? Fantastic. Okay. I still have my planimeter, just like I have my old slide rule. A planimeter is a fantastic invention. It's a mechanical tool where you have a pointer and it's got two arms, like an elbow, and the pointer, you trace around any shape you want that's enclosed, and it will tell you accurately the area inside that shape. It can be any shape at all, and you just trace around, and there's a wheel, and it has also a dial that changes, and when you go around once, you can measure the area of the enclosed region. And what you do typically is do that several times and build it up. Maybe you do it 10 times. So you haven't got to worry about being exactly accurate along the line. You do it 10 times, then divide the answer by 10, and it gives you the area of a peak. And that's how we used to measure areas, okay, before we had computers. So you have luxuries today in what we have in taking our spectra and processing, but it's also easy to make errors with the computers. So when we had to do things by hand, it's quite difficult. You had to always take the data the way you wanted it. And you start to build up big books of spectra because everything's on paper. And data processing, we often use the same computer for data processing as we use for the acquisition. It's nice to have another computer that you could also have the processing software on, so people can keep using the instrument to acquire new data, and then other people can use a different computer to process their data. And it's nice to have network computers. And early on, when we started getting computers, I just loved the fact that I could have a computer in my office and I could connect to the hard drive on my machines and see the data on those hard drives. That was really nice. But then the company decided security was going to be a problem. So they disconnected all the network and we couldn't do that anymore. So it depends on your company. And even today, if you have a network machine, it's possible for the manufacturer remotely to access your machine. And they can do diagnostics on your machine without coming physically to your place to see what's happening. So that's something else that occurs. So the manufacturers can access and they can see the parameters in the machine and see if there's a problem on a particular circuit board or what's happening and know how to fix it. So this is another beautiful aspect of the computers and networking and so forth with machines. The software for data processing, you normally use the software provided by the manufacturer, or also you can use third-party software that has been developed by somebody else. Or you might even be developing your own software because you want to do certain things. So you might have your own software, and a lot of you, developing software as well to do theoretical comparisons and things like that with data. So you can also make software to interpret your spectra. And in processing, we do all kinds of things. We can do smoothing, differentiation in our computer. When I first took my Auger spectra, all my Auger spectra came out as derivatives because I used something called a lock-in amplifier. A lock-in amplifier is a device that actually electronically produces a derivative of your spectrum automatically. So when I took my spectra in Auger spectroscopy on a piece of paper, I always acquired a derivative. That's how it was in the early days. And later with computers, people acquired the data in the direct mode because they could take a derivative in the computer. But early on, if I took my data, my Auger spectrum in the direct mode, I have a big background. So it's hard to measure a peak intensity because there's little features on the big background. So Auger spectroscopy did not become popular until we could take derivatives. So that's when in the 60s, we could take derivatives electronically. The Auger spectroscopy really took off. So if I wanted to measure the area under a peak, I would have to integrate my derivative. And we could take the signal coming out of our lock-in amplifier, and we built integrators, electronic integrators that would integrate the signal for us and give us the so-called direct spectrum. So that was another way that we could do things before we had computers. The background subtraction, elemental identification, measuring peak heights, peak-to-peak heights, peak areas, quantitative analysis. Spectrum subtraction is also something that can be very useful when you have, for example, overlap problem or spectrum addition, where you're simulating what is spectrum you would expect to get from a certain alloy. So having reference spectra is very useful because then you can build up examples of what kind of spectrum you would expect to find based on compositions, different compositions, and compare those with your measured spectrum. Curve fitting, that's particularly important in XPS, a deconvolution, and various chemometrics like linear least squares fitting and factor analysis. Very powerful methods, particularly for depth profiling, where they can be extremely useful to improve the quality of your data. Here's an example. I mentioned yesterday about sulfur molybdenum. And this is a part of the spectrum. This is the energy range here from 100 to 200 electron volts. In OJ spectroscopy, you've probably already realized, you normally measure a spectrum from a very low energy, close to zero, up to a couple of thousand EV. And yesterday I mentioned that all the elements, except hydrogen and helium, have at least one peak in that energy range. So by taking a spectrum over a region from almost zero up to 2000 EV, we can, in principle, detect all the elements. So this is just a portion of the spectrum to show you the difficulty of detecting sulfur using the low energy sulfur peak. So this is my sample. And you have to understand what the spectrum of molybdenum would be. And it turns out, by looking at this, if you compare this with a handbook, or you know what molybdenum looks like in the OJ spectrum, you'll notice that this peak here is bigger than what it should be. This is a spectrum from pure molybdenum. And this is one from my sample. And you can see this peak here is a little bigger than what it should be. And if I subtract off my reference from this measured spectrum, I get this amplified by a factor of 2, and this is my sulfur peak that I could then quantify. And the first kind of computer I had was what was called a signal averager. You could put your spectrum out of your lock-in amplifier into this signal averager. And the signal averager, you could divide into 4 quadrants of data. And you can take the data from one quadrant, another quadrant, and then this data processor, you can subtract one spectrum from another. So signal averages in early 1970s became very popular in surface analysis to improve data processing. So this was taken and the subtraction was done using a signal averager. Today with computers, it's much easier to do subtractions and so forth. Smoothing, there are different algorithms that can be used, but in OJ spectroscopy, the one in green is the one that we normally use. So if we take our spectrum today in the direct mode, and we take a derivative using a 5-point smoothing using Savitsi-Golay algorithm to do our smoothing. Okay, typically a 5-point smooth. I also mentioned about sputter depth profiling. Sputter depth profiling, we have a sample that might have different layers. So for example, here you can see these different layers in different colors, different compounds, different materials at different layers in this particular growth. So you'd like to know what the composition is in these different layers to see what's really going on. So this illustrates what you do. Here's your electron beam. The electron beam is going to interact with the surface. There's OJ electrons that we measure. And if you want to look down deep into the material, we turn on an ion beam. And the ion beam will remove material by what we call sputtering. It sputters away material. So the ion beam removes material, and we typically raster the ion beam in X and Y directions to make what we call a flat bottom crater. So we actually have a good alignment of the electron beam with our analysis depth here. We don't want to be looking on the walls of the crater. So we want to raster the ion beam over a small area so we can actually get an accurate measurement of the new surface exposed. So by sputtering, we produce a new surface. We analyze the composition of that surface. We sputter some more. We get a new surface, measure it, sputter some more, measure the new surface composition, which means different depths. In Auger spectroscopy, you can do these together. You can acquire your data while you're sputtering, or you can do them sequentially. You will sputter, turn the ion beam off, measure the spectrum, sputter, turn the ion beam off, measure the spectrum, and so forth. You have that choice how you do it. So this is called sputter depth profiling. We normally use an inert gas, typically argon. Today we have new sources. Argon cluster sources are now becoming very, very popular in doing surface analysis. And I'll come back and talk about that, particularly with XPS. The sputtered area must be larger than the analysis area. That's why we raster the ion beam. It should be a flat bottom crater. But one of the problems is that the sputtering varies for different elements. So some elements in your sample can sputter preferentially compared to others. So in Auger spectroscopy, we're measuring the species remaining on the surface. So if one element sputters preferentially, we're going to see less of it than what we should. So preferential sputtering is a serious problem in sputter depth profiling. Okay. Here's an example of a crater after I finish sputtering on a sample. And you can also, this is something that I recommend that you do. You could do sputter depth profiling. This checks your alignment, see how good you are. And my alignment of my ion beam, my electron beam, and my sample is excellent. Everything lines up beautifully. There's nothing worse when you're sharing instruments. If somebody comes in and changes your ion beam alignment or something like that, because then you're not going to have it set up the way you have it set up. So everything has to be lined up to optimize the analysis. And here's a typical example of a sputter depth profile. This is a very simple one, silicon dioxide on silicon. Over here, we can see this peak-to-peak height measurements, oxygen. And then as we go down into the silicon substrate, it becomes down to 0. And the silicon peak, this is the low energy silicon peak, very flat, and then in the oxide, and it goes up into the substrate. And this is a silicon KL spectrum. Again, constant value in the oxide, and then constant value in the pure silicon. And you can see the difference here in sensitivity factors. One peak is much bigger than the other peak in the pure material. So which peak you select is up to you in doing your analysis. This is an example here of looking at electronic parts. This is a package with wire bonding, and looking at the bonding. This is the boundary here. This is a backscatter electron image. This is a wire. Okay, here that's bonded, and looking at the composition at the boundaries. And this is a good part and a bad part. This is sputter depth profile. And you can see here that the aluminum oxide layer on the aluminum metal is quite thin compared to the bad part. So the bad part has a thick layer of aluminum oxide, which is an insulator, and is going to cause a problem with your device because it's not going to have good conductivity through the aluminum oxide layer. Couple of examples of Auger spectroscopy compared to EDS. This is a reference material which has nickel chromium multi-layers, and it's been sputtered. And this is the wall of the crater. So this is the SEM image here. And down here are the Auger spectra from the nickel and the chromium. So the red in the example here is chromium and the green is the nickel. So you can see these different layers on the wall of the crater. And in EDS, on the right-hand side, you can see that you don't have that same kind of resolution between those different layers because of the electron beam again is scattering and the X-rays are coming out from adjoining regions. So you don't have that same resolution in doing an EDS analysis across these different layers. So the Auger spectroscopy, being more surface sensitive, is going to give you a better indication of the layers than EDS. Factor analysis is a very powerful way for improving the quality of a depth profile. This is an early example, the first one ever done using factor analysis in surface analysis, done by Steve Garrison, published back in 1981. He looked at a cuprous oxide layer. Here, it's cuprous oxide layer, and here's copper. So copper layers and cuprous oxide layers. And as you sputter through this this layered structure, this is the copper signal, and this is the oxygen signal. So you have oxygen at the surface, you have carbon at the surface, and then you have copper. And then when you get into the cuprous oxide, you see a copper and an oxygen peak. Well, the copper peak changes its line shape. The low energy peak changes line shape when you have copper compared to copper oxide. So copper has this distinctive doublet, and when you get into the oxide, it becomes a broader peak, and you don't see that clear doublet. So the line shapes have changed. So you have peak overlap of the different chemistries. And the high energy copper peak is also chemically shifted compared to the cuprous oxide peak. There's chemical information in here. There's chemical information in there. But by putting all these individual spectra at the different depths into a matrix, you can do matrix treatments using factor analysis to see how many components there are in the data. And in this case, you see there are two components, and then you can plot each component separately, and then you can isolate, separate out the different chemistries. So here's the copper in the metal going down essentially to zero, and here's the copper in the cuprous oxide starting off at zero and going up here in the cuprous oxide. So when you have different chemistries, you have peak overlap, chemical shifts. You can actually use chemometrics, factor analysis, for example, to get rid of this overlap problem. So this is a very powerful method for data processing, particularly in depth profiles, to overcome issues like this of overlapping different chemistries. And it also applies when you have overlapping different elements. So peaks from different elements also useful. Here's a linear least squares method. Linear least squares can also be used to get rid of these different chemistries, overlapping peaks and so forth. And shows you here the low energy peaks of the silicon, pure silicon, and silicon dioxide in the spectrum. And again, you can use this to separate out. This is the raw data. This is the least squares fitting. I can separate out the silicon in the oxide layer from the silicon in the substrate. Now, rather than just have a silicon peak that's going like this and so forth, I can separate out the silicon in the oxide from the silicon substrate beautifully with this least squares fitting. Just a couple more examples and we'll finish up. It's time basically to take our break. I just have a couple more slides here to finish up with, I think. And let me see here where I am. If I Would you rather me continue with the last few slides after our break, or would you rather me finish them now before we take our break? Finish it now? Yeah, I think I'd like to do that. And when we come back, we can talk about XPS. Just a few slides. I'll go through them rather quickly. Example of still belted radial tires. Looking at the still belts. And this is an example here of the still belts. And the steel is in rubber. And you want good adhesion of the belts with the rubber. And so the different platings that have been put on the steel, the brass platings are used. And it turns out that if you have copper sulfide present, you get strong adhesion. But if you have any zinc sulfide, you get separation. So you get belt separation. So people that work in the tire industry use Auger spectroscopy a lot to study these belts, these steel belts and so forth that are in radial tires. And here's an example of the sputter depth profile. Okay, and showing the different compositions and showing you what you have on the different samples, the different chemistries and so forth by looking at these different depth profiles on these different materials. Depth resolution. Again, the higher the ion beam energy, the more the impact, the more the change that you're going to have with the surface. The lower the ion beam energy, the better the interface resolution of layers, but the lower the sputtering, because you also have low energy ions that sputter slowly. And also in most instruments, when you go to lower beam energies, the ion beam current also drops off. So on the left-hand side here is just an example of the depth resolution with beam energy. Beam energy 1000 eV beam for the ions, up to 5000 EV beam. And you can see the degradation here of the interface resolution between different layers. And this might have mentioned here that originally, when you went below typically a 500 electron volt ion beam, you had almost no current from your ion guns. Today, we have what are called floating column ion guns that continue to give you reasonable ion beam current when you go down to low energies. And this was a big improvement in the ion gun technology for doing depth profiling and Auger spectroscopy. Another very important development is sample rotation while sputtering. If you're sputtering through multiple layers, up the top here is an example. This is a material that has good depth resolution, but the individual layers, though, are not flat topped and flat bottom. So this is a chromium nickel multi-layered structure. And if you rotate the sample while sputtering, you get an enormous improvement in the depth resolution. Now you can see flat tops and flat bottoms between the different layers. So rotating the sample during sputtering improves the depth resolution. Last couple of slides, just on instrument selection. If you're buying an instrument, some things to consider. Okay, I won't go through these and read them to you. You can read them in the notes. Lots of things to consider. One of the big ones is the type of the energy analyzer. Different manufacturers have different designs of the energy analyzer. And that's one big factor to consider. Also, if you want to do what we call angle resolved Auger spectroscopy, where you're changing the angle of emission, that also is different for different manufacturers. So I didn't have time. I normally teach a 2-day course, you know, basically 10 hours or whatever on Auger spectroscopy. So I can't include everything here in the shorter time period. But there are lots of things to consider. Also the vacuum pumps, the operating pressure, degree of automation, data processing, reliability, and options like you might want EDS on your machine. You might want electron backscattered on your machine, okay? And electron beam scattered diffraction, I mean. This is a electron backscatter diffraction, is something that's also used now in a lot of SEMs, and you can also use this in Auger spectroscopy. Some manufacturers provide these as options. And just a general summary, we can detect from lithium up. We can't detect hydrogen and helium. It's fairly specific. We know what the peaks are. The variation in sensitivity factors, though, can be about a factor of 100. So some elements are easier to detect than others, but the detection limit is typically about 0.1 to 1 atomic percent. The spatial resolution is tens of nanometers. Now, manufacturers will say, spatial resolution in Auger spectroscopy, 7 nanometers, 8 nanometers. It's not. The beam can be 5 nanometers, electron beam, but the scattering in the sample, giving you a signal from nearby, means you're going to have a much bigger area from which you're going to get Auger peaks. So I really disagree with the manufacturers when they say their spatial resolution for Auger spectroscopy is 7 or 8 nanometers because of scattering. And I think you saw examples of that. So you must be aware of that if you're looking at small features, you will get signal from nearby. That's one of the most important things to remember from this course. If you're looking at nanoparticles, you're looking at small areas, is the scattering of the electron beam in your material. The analysis depth depends upon the material and the kinetic energy of the Auger electron. I showed you examples of that. And you can actually measure the analysis depth. You get 95% of the signal coming from 3 lambda. Basically, you have 0 angle of emission, and you can depth profile for greater depths. Quantitative analysis, homogeneous samples are much easier. If you have layered samples, it's going to be more difficult, even when sputtering, because you have preferential sputtering, but you need reliable sensitivity factors. And unfortunately, we don't have reliable sensitivity factors in Auger spectroscopy. The chemical information, the chemical shift, and the changes in Auger line shape can be very useful. I showed you several examples of that, particularly on silicon and on carbon, and also the possibility of beam damage. And you want to keep the low current density as possible, as long as you get a reasonable Auger signal. And that precludes really studies of polymers using electron beams as a probe. Okay, so sorry to go a little bit over time, but that basically completes the section on Auger electron spectroscopy. Very powerful technique for studying lots of materials, lots of semiconductors, metals, looking at layers, films, depth profiling, and so forth. It's a great technique for solving a lot of problems. Thank you.
Thank you very much, sir. That's just a nice talk on Auger electron microscopy. So we have an announcement. As you know, today we have arranged a dinner along with a cultural show. So if you are interested and not yet informed, please confirm your desire to attend that one with the registration office. So now we have a 30-minute tea break. We will be back at 11:10. So please enjoy the tea and come back on time. Thank you very much.
Just want to mention for those that came in a bit late, if you want to download a PDF, a color version, if you go to that first page of the notes with my website, surfaceanalysis.org, and you put a backslash in, or sorry, / and Pakistan, capital P and small letters for the rest of it, .pdf, you'll actually then be able to see the PDF version of the notes. Okay, so
Training course. In this session, we will discuss another very important surface analysis technique, that is X-ray photoelectron spectroscopy. Basically, this is a surface sensitive quantitative technique based on the photoelectric effect, and we can identify the elements. This is a very powerful measurement technique because it not only shows what elements are present, but also the other elements they are bonded to. So I request Dr. Professor Dante Grant to please start the session. Thank you, sir.
Thank you very much. Okay, sorry to rush through the end of the Auger spectroscopy part, but now going to talk about really my favorite technique. I started doing OJ spectroscopy, and but X-ray photoelectron spectroscopy is the technique that I really love. And you'll see why. You know, it's extremely useful. The big difference between the two techniques, really, though, one of them is spatial resolution. We don't have the spatial resolution in XPS that we have in OJ spectroscopy. So that's one of the disadvantages of XPS compared to OJ spectroscopy, is that we don't have the spatial resolution. But one of the advantages that we have is we don't have backscattering. So the X-rays that we're using as a probe, we don't have any backscattering errors in quantitative analysis. So XPS is much easier to quantify than OJ electron spectroscopy, mainly because of the backscattering effect. So just some terminology. XPS, X-ray photoelectron spectroscopy. Yes, it's the photoelectric effect is what we're using. The X-rays are the probe, and we're looking at the electrons coming out of the sample. And the electrons coming out of the sample are called photoelectrons because they're produced by a photon coming in. But this technique is also being called ESCA. It's the original term, electron spectroscopy for chemical analysis. And it's a term that was used by Kai Sigbahn. And that's his photograph there, Kai Sigbahn. And Kai Sigbahn received the Nobel Prize for developing the technique. His father was also famous. He received the Nobel Prize also for his work in X-ray work. And Kai Sigbahn was a very humble person. I had the pleasure of sitting with him a number of times on a bench, chatting with him, and once also with his wife. And you would never know he was a Nobel laureate. I mean, he never flaunted the fact that he was world famous, that he deserved better treatment than other people, anything like that. He was just a wonderful person. He passed away several years ago. The technique is also often called photoemission spectroscopy, and this is a term that is normally used in the semiconductor research. If you're doing work on semiconductors and looking at papers or doing literature searches, you'll find that they tend to use the term photoemission spectroscopy or PES rather than XPS. So that's something also to be aware of. I don't particularly like the term photoemission because the word photoemission implies maybe that you're emitting photons. So I don't like that term, but it is used quite often. In the last decade, there's been a big change in XPS, and we call it hard X-ray, XPS. In XPS, we normally use soft X-rays, and soft X-rays have a lower energy, typically the order of 1,000 electron volts energy. Hard X-rays have a higher energy, typically up to about 10,000 electron volts. And this is a big field now, hard X-ray XPS or HAXPs. It's such a big field that they have their own conferences now on HAXPs. Angle resolved XPS is also a very important area in XPS, where you're looking at the signal as a function of the angle of emission of the electrons coming off the surface, and that's called AR XPS. There's also one aspect called total reflection XPS, where the X-rays are coming in at a glancing angle to the surface, ideally getting total reflection. So the X-rays are not penetrating very deeply into your sample and becomes extremely surface sensitive. So the total reflection XPS is something also which is very, very useful. New machines have come out in the last decade or so called near ambient pressure XPS. People want to look at biological samples. They want to look at samples that are not in ultra high vacuum, that are in some kind of environment. They want to look at maybe liquids and things like that, where you might, in the ultra high vacuum, you'll have evaporation. In near ambient pressure, that's reduced. And you want to examine these kinds of liquid samples and things like that. And some of you are working in the biological fields. And the ambient pressure XPS is something that can be extremely useful. And also ambient pressure Haxby's, in other words, the hard X-rays, also with these higher poorer vacuum near ambient pressure, because the path of the electrons are going to scatter when you don't have an ultra high vacuum. If you have a poor vacuum, the electrons have a certain distance they can travel before they scatter and won't get into the spectrometer. So if you use hard X-rays, they have a higher kinetic energy of those electrons, and they can go a further distance. So you can work at somewhat higher pressures in those instruments. So, and UPS, ultraviolet photoelectron spectroscopy. So rather than using X-rays, we're using ultraviolet radiation, which has a much lower energy, typically the order of 20, 40 electron volts. So we can't probe core shells, but we can probe the bonding levels. We can probe the outer regions of the bonding. And ultraviolet photoelectron spectroscopy, using ultraviolet rays rather than X-rays, gives us a much higher intensity for looking at that particular region than using X-rays. We can still use X-rays, but the ultraviolet spectroscopy has an inherent higher energy resolution, but also much higher intensities. Another thing is, in XPS, you also will detect Auger electrons. So in XPS, the Auger electrons can be a hindrance because they might overlap photoelectron peaks, but they can also be an asset. Auger electron peaks in XPS spectra can be extremely useful in studying chemistry and also where samples might be charging electrically. So the presence of Auger peaks is also very, very useful in XPS. So XPS is my favorite technique. I'm an electron spectroscopist. I'm going to talk about ion spectroscopy on the tomorrow. And ion spectroscopies are also extremely important and very useful and have completely different properties and looking at different materials in different ion spectroscopies. Also extremely useful. I did a lot of work on ion spectroscopies many years ago, but in the last couple of decades, I've really concentrated on XPS and to some extent Auger spectroscopy, but mainly on XPS. Okay. So here's just a simple schematic of the process. And now in this particular case, we're using a soft X-ray as a probe. And a soft X-ray, we're normally talking about energies of the order of 1,000 electron volts, soft X-rays. And I'll talk about the exact X-ray energies later, but of the order of 1,000 electron volts. One thing you'll notice, I'm not using the X-ray notation anymore. In Auger spectroscopy, we normally use X-ray notation, the K, the L, the M shells. In XPS, we normally use what we call spectroscopic notation, the 1s shells, the 2s, the 2p shells, and so forth. So we use this different terminology, but there's an exact relationship between them. So a K shell is identical with a 1s shell. The same with these shells. This is the 2s is the same as L1 and so forth. But we normally use the spectroscopic notation in XPS. So again, we have electrons occupying shells. The soft X-ray comes in, and then the electrons have a certain binding energy. They're bound to the atom by a certain energy. And if this X-ray energy coming in was 1,000 electron volts, there's a certain probability that that X-ray could remove any of these electrons from any of these shells that have a binding energy less than the X-ray energy, in this case, 1,000 eV. So if the S shell's bigger than 1,000 eV, we can't remove that electron. Okay, so any shells that have a binding energy of electrons less than the X-ray energy, we have a probability of removing them. And in this example, I just show you that the X-rays coming in this case, remove an electron from the 1s shell. So this electron then is removed and comes out, and that's the electron we want to measure. And since it came from the 1s shell, we call that photoelectron the 1s photoelectron. So the label is that of the shell from which that electron came. So if the electron came from a 2s shell, it would be a 2s photoelectron. So that's how we label the electrons coming out in XPS. Now, one beautiful thing in with X-rays is the probe interacting with the electron is that when the electron is removed, the photon is completely eliminated. We don't see a photon anymore. We don't have any photon energy. Whereas in the case of Auger electron spectroscopy, the electron that came in to produce the vacancy in the initial shell is still around. Okay, it's still around. And the electron that came out of that shell is also around. But in XPS, the photon's completely eliminated. So that gives us just a single peak for each shell in principle, and makes the interpretation and makes the spectrum much simpler than in Auger spectroscopy, where we have much more complicated spectra. So XPS also has simpler spectra. It has less overlap issues and so forth. And as you're going to see, can be more quantitative. As I said, mainly because we don't have backscattering effects to consider. I'm going to start off with very simple cases and then go into solids. But for an atom, we have the electrons in these orbits. And as you know, the hydrogen, helium, lithium, and so forth have different occupancies of the different shells. So hydrogen and helium, lithium, and so forth. So the electrons can be removed from any of these particular elements. And we don't normally detect hydrogen and helium in XPS because the probability of removing an electron from hydrogen or helium is just too low with a photon of energy 1,000 eV. So again, just like in Auger spectroscopy, we normally start off with lithium as the element that we detect. But each shell in each atom has a unique set of binding energies. So when the photon interacts and electrons are removed from these shells, they're going to have unique energies. So the X-rays coming in have a certain energy. We have a certain binding energy. So that binding energy has to be used to get that electron just free of the atom. And the energy left over will be the kinetic energy of that electron. So it's really a very simple equation for the case of atoms, that the kinetic energy of the electron coming out is just the X-ray energy minus the binding energy of that electron. So it's a very simple calculation, very simple procedure for the case of the atoms. Just a example, so simple, a periodic table, the atomic numbers. This represents the number of electrons in the isolated atoms for these elements also. And we have so many electrons in the different shells for each atom. We know where they are. We know how many there are in the different shells and so forth. And this is a bit hard to perhaps see in your notes. The electron configuration of the atoms, regarded as an eye test, maybe check out your eyes, check out your glasses. But it's basically showing you what I started to show you. This is the 1s shell. Hydrogen has 1 electron, helium 2, and the maximum of electrons in the 1s shell is 2. So when we go to lithium, that has 3 electrons, the third electron has to go into a different shell, and it goes into the 2s shell. And as we go down through the periodic table, we can see how these different shells build up, and we can see the maximum of electrons in the different shells. For example, the 2p shell has a maximum of 6 electrons. And as we go down the 3D, the D shells have a maximum of 10. So this is very useful. And also in the quantitative analysis, it affects the number of electrons in the shells, is also going to give us a different intensity in those peaks because they have more electrons in those shells. So this is something that's very useful. We can see the configuration, and you might be aware of the fact that we have some interesting effects here. If you look at the transition metals here, this is the 4s shell. You can see that as we go through here, the 3D shell and the 4s shell, we have 1 and 2 that it's filled. And as we go down then in the transition metals, 1 electron, 2 electrons, 3, but we jump up to 5. We have 5 electrons here in the 3D shell and only 1 in the 4s shell. Then we have 5 and 2. The same happens up here from 7 and 2, 8 and 2, 10 and 1. So this depends upon the energy of the system. When the shell's half filled, when it has 5 electrons in there, it's half filled, and that is a lower energy. So that's just physics. That's how the electrons occupy these different shells. So all of these electrons in these different shells have their own binding energies. And as long as the binding energy is less than the X-ray energy, there's a certain probability for ejecting electrons from all of those shells in that particular material. Now, the case of molecules, when we go to molecules, we're basically joining 2 atoms together. Something that very interesting happens, that when we form a molecule, the binding energies change between what they were in the isolated atoms. And here I've just got a simple example of carbon monoxide. So when you join oxygen atom and a carbon atom together, these represent the binding energies of the electrons in the oxygen and the binding energies of electrons in the carbon atom. Well, when they join together, we form these different bonds here between the oxygen and carbon. Okay. So these are molecular orbitals now. They're no longer atomic orbitals. We form new orbitals. These are the bonding orbitals. But the interesting thing is that when we do form a molecule, the binding energies of these electrons that we call core electrons, because they're the ones that are closer to the nucleus and are not involved directly in the bonding. They stay with the atoms. So crudely, on the right-hand side here, I just show a diagram showing you that the 2 electrons in the 1s shell for carbon and oxygen remain with those atoms, whereas the other electrons are shared and form the molecular orbitals. So these electrons are called core electrons, just like an apple core. And this is something that's very important. You'll often hear in XPS about core electrons, the ones that are associated with the atoms. But the binding energy of the core electrons change even though they're not directly involved in the bonding. And you'll notice here that when we form the carbon monoxide, the binding energy of the carbon 1s shell actually increases somewhat compared to the pure carbon atom. And conversely, the binding energy of the oxygen 1s shell, okay, decreases. So when you change chemistry, often the binding energies of the core levels change. And this produces the chemical shift. We talked about the chemical shift in Auger spectroscopy, and this shows you about information about the chemical shift that we also have in XPS. So the fact that we've got core levels and they change the binding energy of chemistry is such an important aspect of XPS. So this is the case of a molecule. And then we go to solids. Solids, we have many atoms. Again, we have core levels, which are similar to the atomic orbitals, but again, the binding energies are different from what they would be in the case of the isolated atoms. because we formed a solid. And again, we have the valence electrons, which are also involved in the bonding. And here's an early example of XPS spectra from, this is mercury vapor. So this approximates the atomic mercury. So here's the spectrum from basically the atoms of mercury. And this is a doublet spectrum. And you can see these two peaks here. And down here are the binding energies. Well, when you put the mercury in a solid, the binding energies are different. And the binding energies in the solid are less than what they would be in the isolated atoms. So the binding energies are different in the solid compared to the atom also. And most of the time we're working with solids in XPS. There might be liquids, but we basically have many atoms, many molecules in our material that we're analyzing. And you'll also notice the peaks are broader as well when we go into the case of the solid compared to the atoms. So in XPS spectra, we're measuring the number of electrons as a function of their kinetic energy. And it's always very important to remember that what we're measuring is kinetic energy, the energy of motion of the electrons coming out of the material. And in taking an XPS spectrum, what we're interested in knowing is the binding energy, because the binding energies are unique for each atom and each shell in those atoms. So in setting up an analysis in XPS, we're normally telling the computer to measure a certain binding energy range. So we will say, I want to measure a binding energy range of 0 to 1,000 electron volts of binding energy. So the computer then automatically calculates out what the kinetic energy range should be in your spectrometer to take that measurement. So the kinetic energy is converted into binding energy and vice versa automatically by a computer. And the equation is the kinetic energy. This is the exact equation. The kinetic energy of a photoelectron coming out of the sample is equal to the X-ray energy minus the binding energy. But in a solid, we have to reference the binding energy to a specific level. And it's referenced to what we call the Fermi level. And we also have to make a correction for the work function of the analyzer. I don't have time to go into the details here, but this is the exact equation. But simply you can think about it as just the kinetic energy of the photoelectron is the X-ray energy minus the binding energy. This is the equation for calibrating your instrument. Now, the X-ray energies we typically use in the lab are aluminum and magnesium. These are the two most common X-ray sources that are used in XPS. And I used to always call it aluminium. I've gone back to aluminum, and going from aluminium to aluminum, okay, is not a big deal. So we have aluminium, 1486.6 is the X-ray energy for an aluminium source. Okay, they have that energy. So with an aluminium source, we can probe any shell that has a binding energy less than this value. Magnesium is also used, and it has a lower energy of 1253.6 electron volts. So we can't probe quite as deep in binding energy in the samples with the magnesium. And some instruments have both of these. We have what we call a dual or twin anode. We have the capability to have aluminium and magnesium, and we can easily switch from one to the other using our computer. And you'll see later why we might want to do this. So that's called a dual, D-U-A-L, or twin anode. So these are the energies of the X-rays coming out. And another source in XPS is using a synchrotron. And some of you might be working at synchrotrons. And at synchrotrons, the X-ray energy you can be varied. You can select a certain energy of the X-rays, and this can be very useful to change the surface sensitivity of your measurement by using the synchrotron. Here's a spectrum of silver, and this is pure silver. And I took this over an energy range of 0 to 1400 electron volts. And this is a good energy range to use when you're using an aluminum or aluminium X-ray source. As a matter of fact, I often like to go from -5, just to go beyond 0, where you won't have any signal, -5 to 1400 eV. But anyway, this is the spectrum I get from pure silver in a spectrometer. And this is called a survey scan. I'm taking a survey, and in this region here, I should be able to detect the peak from all the elements in the sample, except, as I mentioned, hydrogen, helium. Well, and some people call this a wide scan. It just means a wide energy range. And you can see these peaks. These peaks are from the photoelectrons coming out of these specific shells. And some of these shells are doublets. And in some cases, the doublets are very close together in energy. In other cases, the doublets are further apart in energy. And I'll talk about these doublets later. And also you can see the intensities are different. So the probability of ejecting electrons from a 3s shell with aluminium X-rays is much smaller than from the 3D shell. Okay. And that's, again, come back to physics. And also in the XPS spectrum, we also have these peaks, and these are the Auger peaks. These are not representative of electrons coming out of shells that have binding energies to these values. So these occur from the Auger process we talked about earlier, where we have a vacancy produced by the photon, by the X-ray, and after that electron is emitted, the photoelectron, the other electrons can drop down and fill that vacancy and emit an Auger electron. So we always have Auger electrons in XPS spectrum. And we still refer to the Auger electrons by their X-ray notation. In this case, these are silver, MNN, Auger electrons. Many different MNN combinations here. We have multiple peaks here from different combinations of the different MNN shells in that spectrum. So this is a typical wide scan survey spectrum. The other thing you'll notice is the backgrounds. The backgrounds here are much easier to see than the case of the Auger spectrum. The backgrounds also occur in the Auger spectrum because we also have the electrons coming out of the sample. And the photoelectrons coming out from these shells, if they come from deeper in the material, because the X-rays penetrate deep into the material, those photoelectrons are going to scatter inelastically and lose energy, and therefore they'll appear in the spectrum at lower kinetic energy. Now, this is plotted in binding energy. So binding energy of 0 to 1400. If I plot in kinetic energy is going to be increasing to the right. So we normally plot the spectrum with binding energy. Remember, we're always measuring kinetic energy. So we tell the computer to scan from 0 to 1400 binding energy, and then the computer calculates out the kinetic energy range to use for our spectrometer. So this background that we have represents 3D electrons that are coming out from deeper in the material. So each photoelectron peak has a background associated with it for bulk material, and the increase in the background, after we go through each photoelectron, we have an increase in the background. And that's because of the electrons coming out from those shells from atoms that are buried. So if the element was only present in one layer, we would have essentially no background associated with it because it is coming just from the top layer. If a certain element is buried, that means that the peak coming out here, the electrons coming out without losing energy, is going to be a lower probability of coming out without losing energy because the material's buried. So if the material's buried, that element's buried, that elastic peak, this one here, if you like, when the electrons don't lose energy, is going to be smaller, and the background will be maybe increased. That's something that people disregard in XPS. but it's a very important thing to look at in a spectrum, the peak compared to the background. So the peak represents the surface and the background represents depth. So this gives information about depth. And this is actually can be used in measuring a depth profile of a composition near the surface. Okay, and I'll mention that briefly later. So this is a typical spectrum. Then I said this is pure silver. And up near zero, this is the valence spectrum, near zero binding energy, taken with the aluminium X-rays. And you can see here zero, this is zero binding energy. And you can see here a small signal, and then you have this other signal here, and this is on silver. And this measured spectrum compares very well with theoretical calculations of the bonding in the silver. And over here on the right-hand side, it's just an expanded region near zero here. This is zero to calibrate your binding energy axis, therefore XPS. Handbooks. There are several handbooks, and again, these are very important. Okay, so XPS spectra of the different elements are published in these handbooks. The one on the top here by Physical Electronics, this is the latest edition of their XPS handbook. There are early editions as well, but this one is really a nice handbook. And if you're doing XPS, you really need this handbook. It has a spectrum on one page from aluminium and the other page from magnesium. And the spectrum with the aluminium is actually from a monochromatic source, which I'm going to talk about very shortly. And is helpful for looking at the intensities of the peaks, looking at overlap issues, helping you decide if you want to use an aluminium source or magnesium source, and so forth. So no matter what manufacturer instrument you have, this is an extremely valuable handbook to have. There's also a handbook put out by JEOL. It's out of print. And this was also put out for the XPS instruments that was sold by JEOL. Another useful handbook for those working in polymers is this high resolution XPS of organic polymers. And this handbook has the XPS spectra at high resolution of many polymers. And if you're working in polymers, it's essential to have basically this handbook. But also it's out of print, but it's been replaced by something perhaps better, that the authors, Graham Beamson and Dave Briggs, since Wiley did not want to republish the book, when they sold all their copies, they didn't want to make any more. They sold the rights back to the authors so they could then publish the handbook basically on a CD. So the CD has all these pages from the handbook, but more importantly, it also has the actual spectra. So the actual spectra are also included on this CD in different formats. Okay, so you can actually import these spectra into your software to compare the spectra from a handbook with your spectra. And there are also 3 published handbooks from Vincent Christ of elements and additive oxides, polymers, and semiconductors that he also sells. Some books again. Well, the book I mentioned yesterday by Dave Briggs and myself that we edited also includes a lot of work on X-ray photoelectron spectroscopy. And this one here I also included yesterday, and also this one as well. And I also have a list of books on XPS on my website. If you go to /XPS_books PDF, you can also get access to many more books as well on XPS besides these 3. There are many, many books written on XPS. And there are also many chapters written in other books as well that include XPS. This may be hard to see in your notes, but this is a table put out by Physical Electronics that shows you the approximate binding energies from aluminium X-rays by element. So here's lithium, beryllium, boron, and so forth, giving you the binding energies where you would typically measure these photoelectron peaks. And as you go to heavier elements, you can see you can probe more shells and so forth. And the numbers in the boxes here are the most intense peaks and the one that you would normally use for peak identification. And then you have the confirming peaks here as well for the other shells. And on the right-hand side here of this vertical line are the energies where the Auger peaks appear from those elements on the binding energy axis. Photoelectrons here, Auger electrons here. The bottom half of the sheet is shown here. You'll notice there's no numbers down here. That's because their binding energies are too big for the aluminium X-rays. We can't probe those shells. There's a limit, okay, based on that photon energy. And again, the numbers in the boxes are the most intense peaks. And again, over here, the Auger peaks that you would get also in the spectrum. And the ones in the box, again, are the most intense Auger peaks as well. And they also have a sheet for magnesium X-rays. And the values here for the photoelectrons are going to be the same. But the Auger energies over here, these are going to appear at different apparent binding energies because we've changed the X-ray energy. So in the photoelectrons always come out at the same binding energy because our equation is kinetic energy is equal to X-ray energy minus the binding energy. Okay. So the instrument's correcting for that based on the X-ray energy. But remember, Auger electrons, their energies don't depend upon the X-ray energy. Okay, they don't depend upon the electron beam energy that we use in Auger spectroscopy, just depending upon the core levels. So Auger electrons have a constant kinetic energy. But the photoelectrons will have a different kinetic energy when we change our X-ray source. So the spectrum is going to be different when we go from aluminium to magnesium. If we plot on a binding energy scale, the photoelectrons are going to be the same places, but the Auger electrons will be in a different place. So having two sources can be useful if you have peak overlap problems. So one source might be better than the other for a particular analysis. That's just the bottom half. Again, the photoelectron peaks on the left and the Auger peaks on the right. Again, surface sensitivity, very similar to Auger spectroscopy, except the X-rays penetrate much deeper than the incoming electrons. And early on, as I mentioned yesterday, that like very end, their vacuum was not very good. And some people thought perhaps that the XPS was not just a surface technique, but more of a semi-surface technique, and would also probe the bulk because of the X-rays. But later people realized that was not the case because it's the electrons coming out that we're measuring. So the kinetic energy of the electrons coming out of the atoms is what is important to determine the depth of analysis. So the photoelectrons that come from near the surface are going to be in our peaks, and the photoelectrons that have lost energy are going to be in the background. So again, just like in Auger spectroscopy, the analysis depth is determined by the electron inelastic mean free path. Hard X-ray photoelectron spectroscopy uses higher energy X-rays, and these are the typical X-ray sources that are used, silver, chromium, and gallium, by these different manufacturers of XPS instruments. And because the X-ray energies are higher, they can probe higher binding energy core levels. So that's one advantage to using hard X-rays, that we can probe deeper
in binding energy, but also we can increase the depth of analysis. So by using hard X-rays, the energies of the electrons coming out of the shells will be higher. The higher the X-ray energy, the higher the kinetic energy of the electrons coming out, because the binding energy is constant. So we can also get information about depth sensitivity, because low and high kinetic energy electrons probe different depths. They have different inelastic mean-free paths. Hard X-rays can also reduce the effects from surface contamination, because we're going to have more signal coming out from deeper in our sample. We're going to be probing a deeper analysis depth. And also with sputtering and depth profiling, it will also reduce the preferential sputtering effects you might have, because again, you're getting signal from a little bit deeper into the sample with the harder X-rays. Also, if you're doing work at a synchrotron, where you might be able to select an energy depending upon the synchrotron, from a low energy of a couple of hundred electron volts up to maybe 10,000 electron volts, you can make the surface sensitivity very different on the measurement. I might have a slide in here or not. Remember yesterday I showed you the inelastic mean-free path reaches a minimum about 50 electron volts kinetic energy. So if you tune your X-ray energy to make the kinetic energy electron coming up from a certain shell, from a certain atom, about 50 electron volts, you're going to make the most surface sensitive measurement possible. So a synchrotron can be very useful for probing right near the surface and also deeper into a material. And this is a book written recently on hard X-ray photoelectron spectroscopy. Just making a comparison here between using chromium and aluminium X-rays. The levels that you can probe are very different. It may be hard to read these, okay? But by using the chromium X-rays, we can probe deeper in binding energy. We can probe deeper in atomic number, higher atomic number by using chromium. So chromium here is shown in the blue, where we can probe deeper shells. So 1s shells, we can probe the deeper atomic number, a higher atomic number with the chromium compared to the aluminium. And down the bottom here shows you a spectrum. This is again silver. This is like the one I showed you here, aluminium, X-ray source. This is the photoelectron spectrum obtained with aluminium. And this is the one obtained with the chromium. You can go down to much higher binding energies and see deeper shells. Okay. You'll also notice that the Auger peaks have also shifted because they have the same kinetic energy. Okay. Whereas the photoelectron peaks have the same binding energies. So these peaks up here, the outer shells, are going to have the same energies. And the Auger peaks are going to move down to a different place. And also we probe the inner core levels. One of the problems, though, when we go from aluminium to chromium is the cross-section reduces enormously. So the signals are smaller. And this just illustrates over here what we call ionization cross-section. This is the probability of removing an electron from a shell. And shown here for different cases, the reds are silver and the blues are for silicon shells. So you can see here, in going from one particular source to another, this is different shells. Here's one of the aluminum shells. When we go to different energies for excitation, we go to harder X-rays, the cross-section decreases. This is a logarithmic scale. So you can see that particular shell here, this cross-section for the 3D shell, which is the most intense shell for silver, goes from this value down to here, a factor of 100 lower. So the probability for producing the photoelectron from that shell with the chromium X-rays is about 1/100th the probability using the aluminium X-rays. So this means the intensities are weaker. The signals are weaker by using the harder X-rays. Okay. And this one here shows you the case of silver. As you go down, this is the case here for aluminium, and this is the case here for chromium. These are the energies of chromium and aluminium X-rays. You go from this place here down to here, again by a factor of 100. So the intensities are much slower. So you scan for a longer time to get a reasonable signal to noise when you're using a chromium X-ray source, because of that fact that the cross sections are much lower. This is an example from some work that I did. This is on a germanium sample that had an oxide layer present. And up the top here, this is a sample using the spectrum here using a silver source, and down here, aluminium source. This was taken in a Kratos instrument where their hard X-rays are produced by a silver source. And if you compare these two photoelectron spectra here of this coarse shell, the two-piece shell of germanium, you can see the spectra are very different. So this bottom one here in red is the aluminium source. And you can see that we have a complex spectrum here. We have 4 peaks. Well, this germanium 2p region has a doublet. So we get 2 peaks from the germanium 2p, depending upon the 2 shells here for the p shell. And we get 2 peaks. But we get 4 peaks in the spectrum. And this is a thin oxide layer. So we have a chemical shift. So this peak here represents the germanium underneath the oxide layer, the bulk germanium, pure germanium. And this peak represents the oxide layer. So we get a signal from the layer. This is germanium signal from the germanium and the germanium oxide. And this is the signal from the germanium in the bulk. And this is the chemical shift I mentioned, that when you change the chemistry, you often get a shift in binding energy. And when you form an oxide, the binding energy generally increases. So you can see the binding energy is shifted. So this intensity here, the area under this peak and the area under this peak, represent how many electrons are coming out from these different compounds, the bulk versus the oxide. And when I change to silver, I'm probing deeper. So now I'm detecting a signal from deeper in my sample. And look what happens. You see, I'm still probing the same thickness of oxide layer on the top, but now I'm probing deeper into my sample because these electrons now have much higher kinetic energies with the silver source than with the aluminium source. So my signal from the bulk is going to increase because I'm getting signal from deeper in my material. So if you have an instrument that has hard X-ray source as well. So on the instrument that I was using, this is a Kratos instrument. I have multiple X-ray sources. I have a dual anode. I have aluminum, aluminium, and magnesium sources. And then I also have monochromatic silver and aluminium sources. So these are spectra that were taken using the monochromatic sources for silver and aluminium. So by comparing these spectra, by comparing the relative areas of these 2 peaks, I can calculate out the thickness of the film. So I could calculate out the thickness of this film, and it comes out to be about 0.8 nanometers is the thickness of that film, 0.8 nanometers. You'll notice that the signal to noise up here is not as good. I scan for a longer time for this spectrum, but also you still have the noise present. But by comparing these, you can do that. And the cross sections have been published here for the different cases. So you can use the different sources for probing these different depths. Very, very useful. Okay. Sample handling. This is a nice example of sample handling. It's from Kai Sigban. And up the top, it shows a spectrum from clean gold. This is a spectrum from a clean gold foil. And these peaks here and these peaks here are the gold photoelectron peaks from pure gold. You'll notice that in the labeling, he's actually used the spectroscopic notation here for some of the peaks, and he's used the X-ray notation for some of the other peaks. But that's not normally done. You normally use the spectroscopic notation for all the peaks that you have. And down the bottom here is a spectrum that's taken after the gold was touched by a fingerprint. So his technician was working on the instrument and he put a gold foil back in to calibrate the instrument to make sure everything was working okay. And what did you find? You found no signal from gold. Now, gold has a very high cross section. You get a very high intensity peak for the 4F shell electrons. But you don't even see a background. You don't even see anything from gold. No indication of gold being present, even though the sample looks like gold to the eye. And this, again, illustrates the surface sensitivity of the technique. So to the eye, it looks like gold. But to XPS, you don't see any gold. You just see the fingerprint. So if you look at the spectrum here, you see silicon, carbon, and oxygen are the peaks. And it turns out that his technician was also working on the vacuum pump. Okay, now you know about the different kinds of vacuum pumps we talked about. The vacuum pumps that he used in the different instruments over the years have changed a lot. In the older instruments, we used roughing pumps and we used diffusion pumps. Oil diffusion pumps, where you boil oil and the oil stream and acts as a pump. So this particular instrument used a diffusion pump, and he was also doing maintenance on the diffusion pump. And when he was refilling the diffusion pump with the oil, he used silicone oil as in the diffusion pump. He didn't use gloves. And he had some silicone oil on his fingers. So when he touched the gold sample, some of that silicone oil from his finger transferred onto the gold, and a sufficient amount to eliminate any signal from the gold. So this is a beautiful slide to use. So if you have somebody that comes to use your instrument and they touch a sample with a finger and showed them this, it basically destroyed the surface, the fingerprint. Now, of course, XPS can be used in forensics for looking at different things like that, for studying contamination and so forth. So you could tell if a person had chips for lunch or something like that, depending if they have sodium or chlorine peaks. The gold peak doesn't show up because the inelastic mean free path is too short for the thickness of the silicone oil film. So the electrons can't penetrate from the gold. The gold photoelectrons are still produced because the X-rays penetrate through the film. But the photoelectrons produced that come back through the film are attenuated. So we don't get any electrons coming back that have not lost energy. And we don't really see any electrons really that have lost energy. So this means the film thickness is the silicone film is quite thick. So we know it's much bigger than, tens of nanometers. Once you get bigger than tens of nanometers, you're not going to see significant peak. So that film is thick, and you get no signal from the gold because of the thickness of that overlay of film. Just like I showed you here, changing the X-ray intensity here, the energy of the X-rays, I should say. I can change the depth of analysis, you see. So if you changed and used a silver source, you might see some gold, okay? Because you're probing deeper. But with the aluminium source, you're not going to see them in that case because of thickness. So this just gives you an indication of the thickness of the contaminant film from the fingerprint. If it wasn't oil, if it was something that was thinner, like I said, maybe potato chips, you might see the gold still, because you know you don't have an oily film which is going to transfer across your surface. So it really depends upon the material and the thickness of the film. Okay. So anyway, it just shows you the surface sensitivity of the technique, and again, how important it is in doing your analysis. So sample handling is extremely important. Here's an example. This is a spectrum that I took on on some carbon fibers. A colleague was trying to prepare fibers, carbon fibers, and he was trying to oxidize them. And XPS is a nice technique to check and see how the oxidation's occurring on these carbon fibers. So in this spectrum here, the early experiments that he did were not successful. I didn't have a significant oxygen peak, but in this case I did. So you can see the carbon peak here from the carbon fibers, and now you can see he succeeded in forming an oxide film on the carbon fibers. But you'll also notice other peaks in the spectrum. You can see other peaks identified here: sulfur, nitrogen, and nickel. So I wasn't expecting to see those. I don't think he was expecting to see them either. They're low concentration. They're of the order of atomic percents of these elements that are present. But I said to him, I said, how did you oxidize your carbon fibers? And I knew what the answer was already, okay? Because I can see these peaks here from sulfur and nitrogen. So it's very likely he used sulfuric acid and nitric acid to oxidize the fibers. So that's what he told me. He was using the acids to oxidize his fibers. But I already guessed that from the spectrum. But then he also had nickel. And I asked him how he oxidized them. And he dipped the fibers in the acid. And I think I knew also what he did. Very bad technique. So he actually used nickel-plated tweezers. And he actually put the tweezers in the acid. So the technique is so surface sensitive that the nickel that came off his tweezers deposited on his fibers. So I knew the answers already. I could tell it was not good experimental technique. It was not good at all. I mean, you never want to dip your tweezers in the acid, okay? And he was a chemist, and he just dipped the whole thing in the acid, basically. But the technique is so sensitive that I can see these low concentrations, just 1 atomic percent, basically, you know, of nickel on the surface, but it's there. So these small concentrations can affect properties of materials. So XPS is very powerful to understand what's going on in the surface region. And as I mentioned earlier, one of my other colleagues had given me these samples where he was putting coatings on and using EDS, and he could not see the coating. And he wanted me to check if a coating was present. And I could do that and see the coating was present, but I could not see his fibers. Okay. And his actual were quite good. His were clean, okay, in growing his fibers. So it's a good sort of forensic study also, or technique. And then this is a rather simple spectrum, but it shows you that the sample preparation is that he used was not really good. Okay. Again, we identify the elements by identifying each peak in a spectrum. So just like in the one I showed you, okay, we identify the peaks. We have the carbon, oxygen, we have the sulfur, nitrogen, and the nickel. And you start with the most intense peak in a spectrum and compare that position with the handbook or the table, like I showed you, that table I showed you, the numbers in the boxes. But the important thing is to look for confirming peaks. to make sure it is that particular element. And also to check the relative intensities, because peak overlap, okay, can occur and the intensities may not be correct. And you continue this until all the peaks in the spectrum are identified. And remember, you have Auger peaks as well. So sometimes people are confused. They can't identify all the peaks because they forget about the Auger peaks. So you must remember the Auger peaks are also going to be present. And as I mentioned, hydrogen and helium are not detected directly with these sources. And quantification uses the areas under one peak or a set of peaks from each element detected. So in this example here, this was done with the software. The peak identification was done with the software. But basically the software, when you're looking at the biggest peak, the carbon peak in terms of intensity. Oxygen, if you're doing it manually, you would look for what element might be present here. And then go through and look at this peak. And you say this is sulfur. Look for the confirming peak of sulfur, which is there. And look for the relative intensities, which are correct. And then this peak over here, nickel, and look for the confirming peak of nickel. And then this peak here of nitrogen. So you look at the confirming peaks and you measure the areas under the peaks. And I'll talk about later how we measure the areas because we have this background that we have to remove to measure the areas under the peaks. And then using sensitivity factors, just like in Auger spectroscopy, we measure the concentrations, which are shown up here in this table. And the fact that a peak is big again doesn't mean to say it's a higher concentration. Okay, it depends on the sensitivity factor. So you might say here, by looking at this spectrum, you might say, oh, oxygen, we have a lot of oxygen, almost as much as carbon. And it's not. You look at the concentration, carbon 73%, oxygen 22%. And I've been to a lot of conferences over the years, and I've heard a lot of people make mistakes. They'll flash up a spectrum and say, oh, we have a small amount of oxygen present or something like that. And on tungsten, where the oxygen signal is cross-section is much, much smaller than a tungsten. And actually, their concentration is probably about 25%. But because the peak is small, they will just say, oh, we have a small concentration of oxygen on the sample. That is not true. Because you must remember that these cross-sections, these sensitivity factors are very important to remember, to include in quantitative analysis. So that's basically what we're doing in the quantitative analysis, and we look for all the peaks. Now, those of you that are got keen eyes might notice there's some other peaks in here that have not been labeled. For example, up here, there's a small peak there. Do you see that peak? There's a peak there. And if I expanded this up, you might say, oh, there's a peak there as well. It looks like there might be a peak here. Well, there's a peak there, isn't there? And there might be some peaks here as well. So there are more peaks in here that are not identified. But I know what they are, and I don't need to put them in. For example, these are the nickel peaks, and these are Auger peaks of nickel. So I don't need to really identify them. I know they're parts of what I already identified. So you have to identify all the peaks. So I didn't label all the peaks, but I know what they are. And this is what the software should do, go through and do this. But unfortunately, the software often doesn't look for confirming peaks at all. And that's one of the reasons the software often makes errors in peak identification. And this is very unfortunate because I've seen many cases where the software has identified a peak as a certain element, and it's wrong. And a customer's been told that you have this particular element present on your surface, and they're scratching their head and can't work out where that element came from. Okay, well, it's not there. Okay, so this happens a lot, unfortunately, that people are given bad information. And you must look for the confirming peaks and check the relative intensities as well. I mentioned about the electron beam affecting polymers. XPS is much better for working with polymers than is Auger spectroscopy. And many, many years ago, I had a student come to one of my classes, and they had done about 6 months analysis on their samples with a lab that has instruments to provide services. So this company didn't have their own instrument. So they had the work done outside at a commercial company. And they came to the course because they couldn't interpret any of the results. And they were Auger spectra. So the person soon learned that they should not be using Auger electron spectroscopy to study their polymers because electron beams destroying them. But the person this lady spoke to at the company, where this company has Auger spectroscopy, XPS, ion spectroscopy, SIMS. It's the biggest company in the world for doing commercial surface analysis. The person she spoke to did not either understand the techniques or wasn't experienced enough, and she thought she wanted to do XPS analysis. XPS analysis. But the company, the person she spoke to, for whatever reason, told her, no, you should be doing Auger spectroscopy, which was completely wrong. So this person had 6 months of work done, and at the end of 6 months, couldn't work out anything about the results, correlate them with any of the experiments she was doing on her polymers, and said, I better take a course because I don't understand. So she learned at the course that she was right. Originally, Auger spectroscopy was not the technique. It should have been XPS. But the company didn't know that. The person didn't know it. So this is a problem. A lot of people in the companies are not trained to understand the different techniques, which one to pick. And this person she spoke to may have been experienced with Auger spectroscopy and not the other techniques. So this happens a lot, unfortunately, that you can get the wrong information and get the wrong identification of peaks. Even in XPS, I've had companies that I consulted with and having problems also. And they didn't have their own instruments. And they spent a lot of money having analyses done, and they couldn't work out what was going on either. And that's because they misidentified the peaks in a spectrum. So they were told they had certain elements present, and they were not. And also the reports they received were not accurate. And this is part of a problem with cut and paste. So when you have these commercial companies that are doing analysis day in and day out and sending you a report, they're often using a report from a previous client and cutting and pasting things. So they had wrong X-ray sources, and I could tell what the X-ray source was based on where the Auger peak was. So I knew the X-ray source was not what they said it was because of where the Auger peaks were. So the cutting and pasting is a big problem in making reports. So if you're doing that, you've got to be very, very careful with that, so you don't make errors. Some problems in identification of elements are listed here. Peak overlap. Again, by looking at the relative intensities of the peaks is important. Maybe change your X-rays. If you have different X-ray source, change your X-ray source and see what you get. The peaks, if there are Auger peaks overlapping, the Auger peaks will shift in the spectrum, and maybe you don't have that issue anymore. Maybe change the analyzer resolution. In XPS, we can easily change the analyzer resolution to get sharper peaks. And if the peaks are overlapping, we can improve the analyzer resolution to see if we have different structures in the peaks, to see if we have different elements, maybe from overlapping or different chemical states as well, or use a different technique like Auger spectroscopy. And if the sample charges electrically, the peaks are going to shift and broaden, just like I showed you in Auger spectroscopy. And if you try to identify the elements without correcting for charging, you'll get the wrong peak identification. So you need to reduce the charging or allow for it and correct the energy axis before you do peak identification. And of course, as I showed you, chemical effects give you extra peaks due to binding energy shifts as you saw in the case of the germanium oxide film on the germanium. So the chemical shifts are also very useful in XPS, but can provide difficulties for software. The software might think you have a different element present. Here's an example of changing the X-ray type. This is from a dual or twin anode, an aluminium and a magnesium source on copper, just to show you the difference. Here's aluminium. This is binding energy. Here are the main peaks, the 2p doublet from copper. And we also have our copper peaks up here. These are the Auger peaks from copper. We also have what we call satellite peaks, and I'll talk about those later. Magnesium, these are peaks here in magnesium, the 2p peaks. And we have the other peaks up here, the same binding energy. But look, the Auger peaks have shifted in the spectrum because they all have the same kinetic energy. So this exposes this region here in binding energy by using a magnesium source to see if some other element might be present in this region. And that's why the handbooks can be very nice, because the handbook mentioned one page has the aluminium source, one has the magnesium source. You can see where the Auger peaks are. So before doing a study, you might decide that I want to use magnesium as opposed to aluminium, or vice versa, or something like that. You'll also see here over this energy range, I can probe deeper, the 2s shell here. In the case of copper, I can see quite easily. Over here, this would be on this rising background. That's because the energy of the magnesium X-rays is lower in the case of the aluminium. Okay. So having different X-ray sources can be a real asset to help understand compositions and, as I said, reduce overlap problems in some cases. Here's an example of charging. This is a sample of silicon dioxide that I put in a system and took an XPS spectrum from, and that's in the bottom here. And the peaks are rather broad and have a high relative background compared to the peak heights. And up here, there's no signal. This is the 0 level, and this is a 0 level. So these are offset for clarity. And the signals are normalized, so you can compare them. So this is silicon dioxide. It's an insulator, and it's charged. So when the photons come in and the electrons leave the sample, the surface of the sample on the insulator is going to charge positively. So when those photoelectrons come out of the sample, they're going to slow down. They're going to be attracted back towards that positive charge of the surface once they come out, and we'll have a lower kinetic energy. So these peaks are going to be at a lower kinetic energy than what they should be, or on a binding energy axis, they're going to be at a higher binding energy than what they should be at. So this is an issue. So I knew the sample charged, and I turned on a low energy electron beam, which is a normal way for reducing charging in XPS. A low energy electron beam, often called a flood source, electron flood source. They have very low energy electrons, and they will be attracted to any positive charge that builds up on the sample. So where the positive charge builds up, these low energy electrons will be attracted to that positive charge and neutralize it. So simply turning on this source of low energy electrons got rid of the charging issue. And now you can see the peaks here, oxygen, carbon, and silicon are appearing at their correct binding energies. Okay, and from where I have no signal, I could tell, and also from these peak energies, I could tell that the sample in this particular case charged to about 90 volts, positive potential. It was a stable charge. If the charge is changing with time, these peaks are going to shift with time also, and you won't get any useful spectrum. If you have stable charging, okay, like this is a stable charge, the question comes up, could I still use this spectrum to do an analysis, a quantitative analysis? Because I know this is oxygen, I know this is silicon, I know this is carbon. So if I shift these peaks to the correct binding energy by shifting the spectrum by 90 electron volts, well, can I still do a good quantitative analysis or not? The answer is yes, you can, because you're measuring the areas under the peaks. Even though the peaks become broader, the areas are going to still be representative of the signal intensities. So you can still do good quantitative analysis in that case. But charge control is something that's important. So the peak shapes are wrong. Here, the peaks are much sharper. And also you notice the background is much smaller in relation to the peak height when you have no charging. The background height versus the area is constant in both cases. It's just that when you sharpen up this peak becomes bigger relative to this same background. What was that? I didn't hear you. Can you come down the front here or? No. No, shifting. There is one difference though, depending upon your instrument. And this instrument does not have a problem. And the problem that could arise is that what we call transmission function. The transmission function tells you the intensity of the signal as a function of kinetic energy. And that is something that varies with kinetic energy. So yes, since I'm measuring these at a different kinetic energy from what I should be measuring them at, the transmission function is going to be different. And that's another factor that affects the quantitative analysis. In this particular instrument, this transmission function is flat. It doesn't vary with kinetic energy. So in this particular case, it's not affected. But in other instruments, it would be affected. So you're not going to get exactly the right answer. So yes. And this instrument that I took these in is the instrument that I know has the best sensitivity factor set. And it's the instrument I normally use for really good quantitative analysis. I know some other instruments don't have good sensitivity factors. I know if I take spectra in those, I'm not going to necessarily have good results. Okay, so yes, you're right. It can affect quantitative analysis, but in this instrument, since the analyzer properties are not affected by kinetic energy, it basically is going to give me the same answer. Yeah. Here's an example of chemical shift. Carbon. So we take often a survey scan to see the elements present. We see we have, carbon present, other elements present, and that's normally taken at a poor energy resolution. We want to see the elements present. And the carbon peak might look odd shaped, but we want to see what elements are present. So we use generally a poor resolution in our survey scan to get good signals to noise. And then if we want to learn about the chemistries, we'll take a scan over a narrow energy range, like here, the carbon energy range, at a higher energy resolution to see the shapes of the peaks better. And you can see in this particular spectrum, I have at least 4 carbon species, 4 different chemical states of carbon. And in this particular case, this is a carbon-carbon peak. Also, carbon-hydrogen is very close. And this peak here is a chemical shift due to a 1 fluorine. This is 2 fluorines. And this is 3 fluorines associated with a carbon. So this is a fluorocarbon. And XPS is fantastic to see the different chemistries of the surface. And by measuring the areas under each of these different carbon peaks by curve fitting, I can see how much of each species I have of these different chemistries of carbon by measuring those areas of the peaks. So if I'm treating a fluorocarbon, maybe to improve adhesion or do something like that on the material, I can see the relative intensities, how they're changing with processing. So high energy resolution spectra are taken to look at the chemistry. And this is, of course, called the chemical shift of carbon. The carbon is shifted from where it would be for pure carbon to different energies based on the chemistry. So fluorine is electronegative. compared to carbon. So fluorine pulls away electrons from the carbon. And just like I showed you in the case of carbon monoxide, when you pull electrons away, the binding energies increase. And you can see it's fairly linear. The increase in binding energy with 1 fluorine, 2 fluorines, and 3 fluorines is fairly linear in terms of the shift. So you can see this. Now, you might also have some components from carbon and oxygen bonds and things like that. So you must use the full information in your spectrum, okay, the presence of other elements to determine the compositions. But this is just a fluorocarbon. And this is a point of interest. If I have a polymer, just CF3 polymer, a lot of the software packages will not identify that as carbon because it's shifted too far away from where the carbon peak would normally be. So the software only looks at a certain energy range for a certain element, and the energy range in that particular software does not include a CF3 range. So if you have just that kind of a polymer, it won't even identify it as carbon because it's shifted out of that range. So this is something that occurs also with the software. And so I've seen that happen also with the different programs. As I mentioned, the intensities are used for quantitative analysis. We have to measure the areas under the peaks to do our analysis. So we have to remove the background signal. And as I mentioned, the peaks represent the surface, and the loss spectrum down here represents deeper depth, the bulk. So we normally use just the peaks themselves to do our quantitative analysis, but we remove this the background associated with these photoelectron peaks to do our quantitative analysis. And this is pure silver. So if I have an instrument, what I would do to check the sensitivity factors is to measure the areas under each peak and compare the quantitative analysis using the different peaks. So if I use 4 peaks, this doublet, this peak, and this peak, 4 peaks, and pretend I have 4 different elements, even though they're all silver, I would expect to get 25% concentration for silver from those 4 peaks. So that's something I do to check how good the sensitivity factors are in an instrument. And that's why when people ask me if their instrument is very quantitative, this is the kind of thing I recommend, is to take a spectrum of certain material, whether it's photoelectrons or Auger peaks, and do this kind of a measurement and see how good they are. And you'll find that in many cases, the sensitivity factors are very bad. And that means that the accuracy of your quantitative analysis is not good. And as I mentioned, off-by factors are 2. So measuring your own spectra, measuring your own sensitivity factors, and putting those into your database is what you really need to do. Or to use theory, and from the theory, make corrections for your analyzer transmission, and also get better quantitative analysis that way. So it's important to know where these sensitivity factors come from. And a lot of manufacturers today don't know where they came from. And the people selling instruments, they don't know where they came from. I gave a talk about 10 years ago at a conference, and this part of my talk was sensitivity factors. Where do they come from and how good are they? Well, I contacted most of the manufacturers of the instruments and asked them where their sensitivity factors came from. And only one responded. And the one that responded is the one that I already knew where they came from. The others didn't respond. And I think they didn't know where they came from. And even the one that responded, I said, I knew where they came from, and I knew they were no good. Okay, because they were taken from old samples, making various kinds of corrections and so forth. and not using beautiful spectra like they had in their handbook. So when you have a nice set of spectra from different elements, you can make your sensitivity factors from those spectra. For example, from physical electronics, that beautiful handbook, they don't use the spectra they measured in their handbook to get sensitivity factors. They're taken from work that was done decades ago, using different type analyzers, different type transmissions from different compounds, all kinds of, ways that they were trying to correct the different parameters. But when they had this beautiful handbook, they didn't use that data to make better sensitivity factors. So the bottom line was, yeah, most manufacturers don't know where they come from. They came many years ago. Those people have left the company, they're retired. Okay, those people have gone. So the people that are working at the company today don't know where they came from. Okay, and the bottom line is they're not very good. So background subtraction is to remove these inelastically scattered electrons from the XPS spectrum, allow us the peak area to be measured. And there are three common ways to remove the backgrounds. One is called linear. Linear is just a straight line between two energies. Another one is called the Shirley, because Dave Shirley came up with this special algorithm for measuring a background. It's sometimes called integral. And this is the most commonly used background. And it's the one that I almost always use in my XPS analysis, is the Shirley background. Another one is two-guard background. And unfortunately, two-guard background, it's a very good background, but it's abused because two-guard background is designed to be applied only in samples or in regions where the energy range is at least 50 electron volts beyond where the peak is. So when you're taking a narrow region scan, you're normally not scanning down over 50 electron volts away from all the peaks. So two-guard is not meant to be applied there, but people still do it, and it's not right. Okay, it's not a good background to use in those cases. So the Shirley background, it calculates a background. And what he decided was that the background produced by inelastic scattering at a specific energy E is proportional to the number of electrons with kinetic energy higher than E within the peak compared to the total peak. So it's iterated. So you measure the background iteratively after choosing two endpoints. And this is generally much better than straight lines, particularly for metals. And here's the original paper from Dave Shirley, where he talked about this particular algorithm. So in going through a peak, you measure how many electrons are above that particular point where you're calculating the background compared to the total number in the peak. And what he's saying is the background is proportional to how many electrons are above that energy compared to the total number in the peak. That's a reasonable approach to determine a background. Here's just a couple of spectra here, showing you the Shirley background. This is a spectrum here. This is a spectrum of carbon from a polymer. And you can see there are at least 4 peaks here. And the Shirley background here, okay, is shown by this line. And this is the energy range over which the Shirley background is calculated here, shown in blue. And over here, in the case of silver, this is the Shirley background. And the Shirley background has this kind of a stretched S shape. Because when he's calculating the background at this particular place here, you see the area under the peaks to the right, to the higher energies, is very small compared to the total area. So the background here is very small. So you see the background is fairly flat. And up here, the intensity is changing rapidly. So now the area above this energy compared to the total area is now getting bigger. And that's why the background's changing rapidly. So when the intensity is changing rapidly, the background's changing rapidly. Then it flattens out again here because now the signal intensity is not changing very much because there's not much more signal above compared to the total area. So the background's very flat. And again, as you go through, the background's changing much more rapidly here. And this is what you get. So what he's saying is that even in the elastic peaks, there is background because some of the intensity here is due to inelastic losses. Some of the electrons that you're measuring have lost small amounts of energy. So there is an energy loss here. So you have to remove that background due to that energy loss. And that's what this is. So this is a Shirley background. This illustrates the comparison of the different terminology. We talked about the X-ray notation in Auger spectroscopy and the spectroscopic notation. And there's an exact correlation between the X-ray notation and the spectroscopic notation. And that's shown here. And you'll see that some of the shells have a subscript. The S shell has the subscript comes from quantum numbers, and I don't really have time to go into that in detail. But the S shell always has a associated quantum number of a half. So we normally leave that off. So we normally just talk about a 1s shell, a 2s shell. But the P shells split into two, and they have subscripts of 1/2 and 3/2, depending upon which particular shell we have. Okay, and then the D shells also split into two, and the quantum numbers associated with them are 3/2 and 5/2. So the subscripts that we use come from the particular quantum number, particularly this J quantum number that we calculate for these different shells in the atoms. So the S shell is normally a single peak. The P's, the D's, and the F's normally split into doublets due to what we call spin orbit splitting, and give us these doublet peaks. This just shows you here this effect. These are spectra from the different elements. This is an S shell. So this is a 1s shell. It's a single peak. Okay. So that's a single peak. This one over here is a P spectrum, a P shell. So these are P shell electrons coming out here. And the subscripts are 1/2 and 3/2 for these two peaks. So the 1/2 is this peak and the 3/2 is this peak. And you also see some particular structure here associated with this particular material. And the relative intensities of these peaks, the P shell peak should be 1 to 2. So this peak should be twice as big an area as this peak. And that's illustrated up here. The subshell of P shell, the ratio of the areas is 1 to 2. The D shells should have a ratio of areas of 2 to 3. So this area to this area should be ratios of 2 to 3. And in the F shells, the ratio should be 3 to 4. So this should be 3 to 4. So when the shells are filled, you should get these ratios of the relative areas. And this can be useful because if you have a doublet, like a P shell, you would expect to see the ratios 1 to 2. And that can help you identify what the element might be because of the ratios of the areas of the peaks. Yeah, I know it's a P shell. I know it's a D shell. I know it's an F shell based on their relative areas. Now, of course, if it's an S shell and a chemical shift, that's not going to apply. But basically, this is important to know this, that the relative intensities of these doublets. Okay, remember the S shell, single peak, the P's are 1 to 2, the D's are 2 to 3, and the F's are 3 to 4. And easy to remember, because all you do is increase by 1. 1 to 2, 2 to 3, and 3 to 4. Right, the sensitivity factors. In some of the software, for example, this peak, if you use this peak for quantitative analysis, it has a sensitivity factor for the this peak. it also has a sensitivity factor for this peak. So the sensitivity factor for this peak is going to be a half the sensitivity factor for that peak. So if I use this peak for quantitative analysis or this peak for quantitative analysis, I should get the same answer. Now, if these peaks are very close together and they're not split well, then basically you have a sensitivity factor for the combined doublet. And a lot of the software packages will have that as well. So you'll have a sensitivity factor for the doublet, but when the peaks become widely separated, you'll have sensitivity factors also for each of the individual peaks, but not all manufacturers give you that. Okay, so it's also something to be aware of. As a matter of fact, if I go back a fair way here, just to tell you, this one, when I did the peak identification in this program, it identifies the peak, and then it puts a background associated with the peaks. And when it looks at the nickel over here, it didn't do the doublet. It just put the one peak in, but used the sensitivity factor for the doublet. So I would get the wrong concentration because my area is too small when I'm using the sensitivity factor for the doublet. And this is a common error I find a lot of people make, that when they have doublets where the peaks are maybe close together, that when their software makes a peak identification, it might use one peak only, but it defaults to putting in the sensitivity factor for the doublet, the combined area. So you must change that to be just for the one peak, or change the area to be for the doublet, then use the sensitivity factor for the doublet. So that's a common mistake that people make in doing their quantitative analysis. You must match the peaks you're using with the sensitivity factor that you're using for quantitative analysis. So yes. The chemical shift, I already showed you that for the carbon and fluorine, how that the binding energies of core levels increase when you take away electrons from an atom. And conversely, the binding energies decrease when valence electrons are added to an atom. So as you take electrons away because of electronegativity differences, you're pulling electrons away from an atom, the binding energies generally increase. You notice I use the word generally. When I use the word generally, it means, maybe this doesn't happen all the time, because otherwise I wouldn't need to use that word. But it turns out in some elements, when you change the chemistry, the binding energies don't shift. And there's several elements where this happens. And I did quite a big study on barium many years ago in terms of fermionic emitters and cathodes. And in case of barium, the barium binding energy does not change significantly with chemistry. When I go from barium metal to barium oxides, the binding energy is essentially the same. It does not shift. So this is an issue that happens in several cases, that the binding energies don't change significantly. Now, of course, in the spectra I will see oxygen. So I know I have barium oxide. So this is an issue. But you know what? I mentioned about the Auger peak, and I'll mention it later, but there's a term that's called the Auger parameter. And that is the energy difference between the photoelectron peak of barium, for example, and the Auger peak of barium, the main peaks. And that energy difference does change when you change chemistry. So the Auger parameter does change when you change chemistry. And that can be extremely useful for helping understand the chemistries. Because the Auger peaks in general shift much more than photoelectron peaks. So that makes it very useful. So the Auger parameter was a solution to that particular study as well to help understand the chemistries. Well, that's another issue, whether what's going on with the oxygen. Because yes, you might have an oxygen on the surface that's a contaminant on your material. So that's another concern as to what you have. So if you have a different X-ray energy, you can take a spectrum of different X-ray energy and see if it changes. Just like I showed you from the germanium oxide, okay, the relative intensities change. But that's a big problem. Another thing you can do is do angle resolve work, where you're enhancing the surface sensitivity to see if the surface is different. So yes, contamination is an issue. It makes an uncertainty in the analysis, yes. My course I normally teach on XPS is 3 full days. Okay. So it goes in a lot more of those kinds of details. So I can't, go into that depth, but there's a lot, there's a lot to understand. I could teach an XPS course probably for a month. Okay. Basically doing a course on my whole book or something like that. There's so many different areas of in XPS as well. And I've been doing it, for 50 years. So I've got a lot of experience in the technique and things like that. And over the years, I've seen all kinds of horror problems and misinterpretations and things like that, and inaccuracies in publications. And just as a matter of fact, just to tell you that when you read the literature, don't always assume that what you read is correct. Even in highly respected journals like Nature. I can tell you that approximately 1/3 of the papers published in XPS are wrong. 1/3, including Nature. And several, about a dozen of us that are fairly experienced in XPS that are involved with developing standards, we thought we should write to the editors of some of these journals and publish maybe a letter to the editor pointing out the errors in general that occur in journals. Well, the first one we sent it to was Nature, of course, because Nature had some very serious errors. And the editors, of course, never wanted to publish a paper that would point out errors in Nature. So none of the journal editors really wanted to publish our letter. And we finally published it in a journal which was not so involved with surface analysis. And it's been referenced many times. But some of the errors are quite bad in terms of interpretations and so forth. And it's very unfortunate. And today, a lot of researchers are using many techniques. And when they publish a paper, they're using many techniques. And when the editors of the journals send out papers to be refereed, a lot of the referees are not experienced in many of these techniques. And that's a serious problem today. And a lot of people don't want to do their job. If you're a scientist or engineer and you're asked to referee a paper, you should do it when you can. A lot of people won't do it. And it's hard to get referees. So if you've got a paper that's using, say, 4 different techniques, ideally you'd like an expert in each of those 4 techniques to do it. Well, the journal editors give up after a certain time because they can't get the people. And the people doing the refereeing may not understand the technique. So the interpretation of the person doing the work, they don't know what they're doing because the computer's giving them a certain answer, and that's what they assume is correct, and putting it in their paper, and nobody picks up on that error. So it's something that's been growing and is extremely dangerous and serious today, is the number of mistakes in the literature. And over the years, enormous number of mistakes. Another one that happened many, many years ago, one of my colleagues was asking me to determine low concentrations of oxygen in tungsten. Because when you have low oxygen, different oxygen concentrations, you can change the structure of the polycrystalline materials. And the literature said you can never get below a certain amount of oxygen. in these crystals. When you're growing these crystals, you normally don't have a good vacuum, maybe. So depending upon the rate of growth, you might get some oxygen incorporation in your films. So that community was misled by a publication that said you can never get below this amount of oxygen in growing these films. Well, what if you grew them in ultra high vacuum? Okay. Or what if you looked at pure tungsten? Well, tungsten's quite reactive, so it's going to absorb oxygen also quite quickly, maybe from your vacuum system if it's not very good. It turned out that the peak that they used as a chemical shift of tungsten to say that there was oxide always present in their films was actually a peak from pure tungsten. And that shift was not the correct shift of tungsten oxide. So when they asked me about it, I looked at it, I said, no, they're wrong, because that peak is not the right energy, and that peak is also pure tungsten. But already in that field, many people believed that you could never get rid of a certain amount of oxygen. So, you know, these things, people read a paper, they accept it as truth and goes on from there and just gets perpetuated, unfortunately. Okay. So here's an example of a chemical shift. Again, the same spectrum I showed you earlier. In this case, I'm using a linear background, because in polymers, linear backgrounds often work very well. I could use Shirley. In this case, it's going to be almost basically also a straight line. And you curve fit. So curve fitting is done in XPS a lot. And the areas of these peaks here give you the relative concentrations of these different chemistries. Chemical shift is an example of corrosion and charging. So in this, on the left-hand side here, it shows you raw data. Up the top here, this is aluminum. And this is raw data. And these are some samples that I studied. And up the top here, these are peaks from the aluminum. You can see I've got two peaks. And these peaks, basically, this is from the metal, and this is the chemical shift of the oxide. So I could measure the areas under these peaks and get a relative idea of how much of each I have, or at least compare them with other samples. And this is the raw data of another sample. Well, you can look at this and say, oh, okay, in this case, this peak corresponds to this one, but it doesn't. There's a charging problem here in the samples. So in this sample here, charging occurred and the peak's at the wrong place. So this peak here shown in green is actually the oxide peak. And the charging was just coincidentally the amount that would put this peak aligned with the metal peak. But in the spectrum, you'd find that all the peaks shifted by the same amount, and they're not accurate. So carbon and oxygen are good ones to check, because oxygen doesn't change a lot with chemistry, not this much. It changes somewhat. Carbon also changes, but the carbon contamination on the sample doesn't change. So by looking at all the peaks, they all shifted by about the same amount, so you know it's charging. Also, this peak is broader, and this peak is basically the same as this one. This is the oxide peak. So you can charge correct. So this is the metal, this is the oxide, and then this is the charge corrected oxide. So this was an alloy reference. This was just a sample with a natural native oxide on it. And this is a sample that was exposed for 3 months to a corrosive environment. So it's an example of corrosion, but the sample charged and in the analysis, and you must correct for that. Otherwise, you get a misinterpretation due to charging. So you must be very careful to distinguish chemical shifts from charging. If you have both occurring at the same time, it makes it much more difficult. Okay. to do our analysis. Okay, just a couple more slides here. It's time for our break for lunch and prayers. And since I was just talking about chemical shift, this is an example of lithium battery electrodes. This is a very important area of research today. And XPS is used extensively for studying lithium chemistries, and surface chemistries, and so forth. Lithium oxides, hydroxides, and so forth. Without air exposure and with air exposure, showing you how the peaks, here they fit these peaks with different chemistries, and over here how it's changed from one particular case with different compounds to essentially almost one compound. And lithium has a low binding energy, it has a low cross section, but it's very useful. XPS is very useful for lithium research. Okay, and then plasmons, I talked about those yesterday, about these extra peaks that we get. This is aluminum metal. We have the extra plasmons, the bulk plasmons and the surface plasmons. Okay, and this is aluminum oxide. I didn't have an oxide yesterday for the Auger spectroscopy of aluminum. I had it for magnesium, but here's the case of aluminum. There's a shift in the peak position. If you look at the energy of these peaks, the aluminum oxide peak is shifted to higher binding energy. It's also broader. This is generally the case in an oxide, the peaks are broader, but I don't have these plasmons. I have loss structure. I don't have these plasmons. So in XPS, by looking at the spectrum, if I see plasmons, I know I have some metallic character. Okay, if I don't see plasmons, I know I don't have metallic character. So you learn by using as many things as possible in your spectrum to understand the chemistry. I think it's a good place to stop right now. There are many other effects. I've got a couple more of them as well in the photoelectron spectra to help you understand chemistry, but I think it's time we should stop. Okay.
Thank you very much, sir, for such a comprehensive talk on XPS. So now we have a lunch break. We'll be back at 2 p.m. So during the lunch session, we will also have a poster competition. So all the candidates with the posters are requested to be there at 1:30. And at the end of the today's session, that probably will happen like 4:15. We have a group photo. Please make your presence. Ensure your presence for the group photo. Thank you.
Yeah, one more out for Mary. Got my sheet here.
We'll start again with the previous session. I request Dr. Jonty Grant to start the technical session. And one more announcement. At the end of the session, we have a group photo. Please make sure your presence.
Thank you. Okay. Thanks very much. Okay, well, let's continue on. Another effect that you can observe also in XPS is called shakeup. And this is observed in unsaturated polymers, particularly in aromatic compounds. So it's not a chemical shift. It's just the fact that the electrons coming out of the material lose a specific amount of energy and give you a small peak here compared to the main peak. And this is a pi star shakeup feature that you'll see in a lot of the aromatic polymers. And also you get the same kind of effect, the shakeup in copper compounds, particularly, for example, cupric. Cupric compounds of copper also have characteristic shakeup peaks. And also I put this in purposely because occasionally you'll see spectra plotted in a different direction. So this spectrum here, the binding energy here is showing increasing to the right. So this is something you'll be aware of. Sometimes you'll see this. And I've seen it in one publication where they had both formats. The binding energy increasing to the right, binding energy increasing to the left. It makes it very difficult then to go through and read the paper.
And the editors should insist upon one particular way of plotting, at least in one paper. And the conventional way is to plot with binding energy increasing to the left. But a lot of the intensity is taken out of the main peak into these shake-up peaks for both of these copper cupric states. And this is very useful also in understanding the copper chemistries. Instrumentation. This is just a simple instrument, no cables on it, showing you analysis chamber, a introduction system here, sample transfer. Samples are put in through a door. We have a gate valve. We evacuate this region here, typically using a turbomolecular pump. And once it's evacuated, we open the gate valve and move the sample into the analysis chamber and transfer it to the manipulator so we can move it around. In this case, this is the analyzer. This is a specific kind of analyzer. And the vacuum chamber also looks like the shape of the analyzer. It's a hemispherical analyzer, which is the analyzer used in almost all XPS instruments to measure the spectrum. And each of the hemispherical analyzers has an input lens, which is extremely important in acquiring the spectra. Also shown on here is a dual anode X-ray source, and they're often mounted on a bellows so you can move it in closer to the sample to get more signal. So you can easily switch between one source and another to change from, for example, aluminium to magnesium X-rays. And here's an example of a twin or dual twin anode, typically made of copper. These two flat faces, anode 1 and anode 2. The copper is deposited with aluminium, for example, and magnesium on these different faces. And when we want to change the X-rays, we just turn on one filament. This filament hits the aluminium side, anode face 1, and this filament would hit the anode face 2. So it's very simple to switch between the different X-ray sources. And of course, you must cool these with water. So water is continually used to cool the anode, otherwise it would melt. And the actual spectrum that we get is combined of a K-alpha-1 and K-alpha-2 X-ray lines. And besides the characteristic lines, we have other lines. We have some satellite peaks at known energies, but we also have this continuum background at all the different X-ray energies all the way up to the potential between the filament and the anode. And this is called Bremsstrahlung. You may have already know about this. So the X-rays are not just one energy. They're, we have the main peak, we have some satellite peaks, plus we also have this broad background of X-ray energies. This here illustrates the relative intensity of the different satellite lines we get. So this is aluminium. This is the main line, the K-alpha-1,2, given 100 units of intensity. We also have other X-rays coming out at these relative energies to the characteristic line with these intensities. So you can see you'll get an extra peaks in a spectrum from these X-ray satellites. So that's something to be aware of. Using these non-monochromatic sources, we have other X-rays besides the characteristic line. So besides 1486.6, we also have X-rays coming out at these higher energies from these types of sources. Here's an example again, showing you the spectrum here. And you can see the doublet, you can see the other peaks up here. This is copper with the Auger peaks. And these extra peaks here are satellites. So you have a satellite, and it's not resolved here, but this K-alpha-4 satellite is about 1/10 the intensity of the main peak. So you get these extra peaks with these sources. But we know we have them. We know the intensities. We know where they should be, and we can allow for that in doing identification of an element. The next thing in X-ray sources is to use what's called a monochromatic source. Monochromatic means one color. So we don't have any of these satellite X-rays, and we don't have any Bremsstrahlung. We just have one particular energy. So this gives a simple spectrum, no satellites and no Bremsstrahlung. And the monochromatic source is obtained by using a crystal of quartz that basically selects the region of the K alpha 1,2, and that monochromatic beam of X-rays then is used onto our sample, and the photoelectrons come into our input lens and into our analyzer to obtain a spectrum. So since I'm a little bit behind time, I'm not going to go into a lot of detail about these things, but one point that's important to note is that the X-ray line width is sharper, about 0.3 EV, than it is with a conventional source. Conventional source, the aluminium, is about 0.85 EV in width, and magnesium is a little bit sharper, 0.68. So using a monochromatic source, you're also sharpening up the X-rays that you're using to produce the photoelectron spectrum. And here's an example. Using a monochromatic source, we have no satellites. So it's much easier to analyze the spectrum when we have a monochromatic source than we do with the conventional source. And of course, they cost more money. So more expensive to have one of those than a dual anode source. Synchrotron sources. Over the years, the intensity, the brightness of the X-ray sources, synchrotrons, has improved enormously. This is logarithmic scale here. And this shows you third generation synchrotron sources. And over here are newer sources as well, showing you again enormous increases in intensity of these synchrotron sources that can be used in studying surfaces of materials. And there are many synchrotrons around the world, and people are still building synchrotrons, very expensive to build, but very useful in lots of areas, including surface analysis. And to acquire a spectrum, what we do is we fix what's called a pass energy. So we fix the resolution of our spectrum all the way across the spectrum. So this is fixed by selecting a certain pass energy of electrons that goes through the hemispherical analyzer. So this might be 100 EV, which is a typical pass energy, and that determines the spectrum resolution based on our analyzer. So for a survey scan, we use a high pass energy, and a lot of the instruments go up to 150, something like that. Some go 180, some go 200 EV. So a high pass energy is also used in a survey scan to see what elements are present in the material. So the resolution on the spectrum itself, energy resolution, is not going to be great. We can't understand chemistry. We can just get the elements. And if we want to get a higher energy resolution, we use a smaller pass energy. So typically a survey scan will be taken at a high pass energy, and then a chemical analysis over a small energy range over one particular peak, like carbon or something like that, is taken at a higher resolution by using a smaller pass energy. And we take a spectrum. After we fix the pass energy, you select that. We take the measure of the spectrum by retarding down the electrons that come into the analyzer. So the electrons going through the analyzer always have that same pass energy that we select, and we scan the spectrum by changing the retarding potential in this input lens here. That's how we obtain a spectrum. The line shapes that we get in XPS are typically a combination of what we call a Gaussian and a Lorentzian shape. And this just compares a Gaussian and Lorentzian. The Lorentzian line shape has a broader tailing here, and that's shown in this red spectrum, compared to the Gaussian. The natural widths of core levels are Lorentzian shape. And the analyzer gives you a Gaussian shape. So if you use a high pass energy, the shape of the peak that you have is going to be more Gaussian. If you use a high energy resolution, the peak shapes are going to be more Lorentzian. So if you're doing curve fitting to isolate different chemistries, you select different line shapes. And you must be able to select a line shape based on the combination of these two, depending upon which ones dominate. So at high pass energies, poor resolution, the peak shapes are going to be more Gaussian. At lower pass energies, higher energy resolution, the peaks are going to be more Lorentzian. And you can use combinations of these in curve fitting. There are also other line shapes that are used in analyzing data as well than these simple line shapes. This just illustrates using a different pass energies on a silver spectrum. This is obtained using a magnesium source. So this is the silver 3D doublet. Remember, the ratios of the area should be 2 to 3. This is the highest pass energy in this instrument, 188 electron volts. When I change the pass energy down to 47 electron volts, you can see the peaks become sharper. And if I go down to a very small pass energy at 3 eV, the peaks are now much sharper still. So now I'm going from a broad peak to a sharp peak. Also, these are going to be more Gaussian shaped because the analyzer is making the peaks more Gaussian shape. But down here, the analyzer is not contributing much to the actual line shape, and these will be more Lorentzian line shapes. You'll also notice the satellite peaks. Okay, and each of the peaks has its own satellite peaks. This peak has these two satellite peaks, and this peak has these two satellite peaks, and so forth. Here you can't resolve them. Here you can start to see them as the doublet, and down here, finally, you can see them are quite well resolved. So the high pass energies are used to get high signals of noise for detection, and lower pass energies for understanding chemistry. And this is a very low pass energy, just put here for illustration. And typically, if your instrument's 188 eV pass energy, is the maximum for survey scans, you're going to use something like 47 EV typically for most of the line shape analysis, something like that. It just depends on your sample and what you need to know. Now, the peaks also decrease in intensity when you go to smaller pass energies. And here I've normalized them to the same heights so you can compare them more easily. Okay, so when you improve the resolution, you lose signal intensity. Just to show you a couple of examples, this is a survey scan taken on a certain semiconductor. Okay, and you can see some of the peaks I've labeled. And here's gallium, a gallium doublet down here to the 2p doublet, indium, and there's gallium, indium gallium compound here, and indium gallium nitride. And this is a survey scan. And I want to put this in to show you an example of different conditions for analysis. So look at this one and compare this one and see if you can see any difference between the two. It's in the labeling up the top. I just want to point out that these spectra, they're actually slightly different samples, similar compositions, but the spectra look rather similar. Okay, they both look rather similar, don't they? But the big difference is up here, it talks about the time, 125 minutes to acquire this spectrum, 2 hours. And in this spectrum here, 5 minutes. So I acquired that spectrum in 5 minutes compared to the other company who acquired the data in 2 hours. And my colleague was having all his work done with this other company. That machine broke down. He asked me, could I help him by doing some analyses? And I said, yes, I can help you. So I did some analyses. And I also asked him to let me know, compare my result with the other place that was doing analyses. And I was surprised to see it took them 2 hours to get essentially the same information that I got in 5 minutes. And if you're paying to have somebody do it, a lot of labs will charge you $500 an hour, you know, to do your analysis. So this would cost $1,000 to do, and mine was basically 5 minutes. A big difference in time. So this basically comes down to knowing how your machine works and what pass energy to use, what step interval to use in your taking your spectrum, and how much time to use to take your spectrum. And I see this a lot, that people aren't using optimum conditions to acquire their spectrum. So you need to understand how your instrument works so you can get the best results in the shortest time. Okay. Also, we often want to look at small areas, and there are different ways that manufacturers have approached that. One way is to focus the X-rays down to a small area. And that is the technique that's used by physical electronics in their instruments, typically down to about 10 micrometer size, and also using a zone plate of the synchrotron, where you can get about a factor of another 100 down to about 0.1 micrometers, which is the current limit for spatial resolution in XPS. So the spatial resolution in XPS is not as good as in Auger spectroscopy. Other ways are to use different things here, changing an aperture in the lens and so forth, I've listed. But the techniques that companies typically use today to get good spatial resolution, in the case of Kratos, they're using an imaging mode and an analyzer. They got a special mode that they're using. It's an imaging mode, a different type of analyzer that's used in conjunction with the hemispherical analyzer. And also Thermo has a microscope mode for measuring small areas, imaging actually. And Cyanta has an instrument where they can also get down to about 1 micrometer. And also they can operate that in the an imaging mode, which gives you a slightly better imaging resolution. So the modern instruments can get down to about 1 micrometer spatial resolution. That's the limit currently in the lab for doing XPS. And a synchrotron, about 0.1 micrometers. We can't look smaller than that. This is an instrument. Again, this is a bit more complicated than what I showed you earlier. Hemispherical analyzer over here, dual anode here. This is a monochromatic source. The crystals are up here. This is the rod where you transfer the samples into the analysis chamber through a load lock that you can't see. A manipulator here to move the sample around to get different points of analysis. And this is an ion gun for sputtering, for doing depth profiling. And also has the capability of using different gases on this particular ion gun. In the imaging mode, where you focus the X-rays down to a small area, the X-rays are produced from an electron beam. So an electron beam is used onto an anode, and it's scanned across the aluminum anode. And as it's scanned across the aluminum anode, X-rays come off. And these X-rays that come off are impact on this monochromatic crystal, quartz crystal, and the X-rays coming down to the sample are monochromatic. And when you scan the electron beam on the anode, it's going to scan the X-rays across the sample. So that's how this manufacturer does imaging, by scanning the electron beam used to produce the X-rays. And just like this is a mirror to give you a scanning X-ray beam for imaging. The imaging mode in a Kratos machine is shown here. They have a special analyzer. They call this a spherical mirror analyzer, and it works quite well. And rather than going through the hemisphere, they're going through, electrons are coming through this, this spherical mirror and giving you an image over here on a microchannel plate. And the first model of this that came out, I was very impressed. I could not believe it, how quick it was to take an image of a certain element on a sample. They just move the sample, the image moves very quickly, very high signal, high count rates. This is an example of scanning the X-rays across the surface. And this is also allows you to look at the scanning X-ray produced electron image. So this is like an SEM type image, but as you scan the X-rays, what you're doing is looking at electrons coming off and measuring the total electrons coming off. So it gives you an idea of different contrasts, maybe different compositions in different places on your sample. And then you can do analyses in different places. And over here is a map showing you in different colors the composition of different places. Tantalum's in green, here and here. And you can see the gold is in red and silicon's in blue. You also notice this inner ring here of tantalum, which you don't see here in this particular map over here. So it is the example of a 10 micrometer wide tantalum ring here on this particular device. Also, you can use sophisticated data processing to improve the quality of images. This just shows you a case on the top left here of raw data. This is what physical electronics, they have that phi symbol as their trademark. And what they wanted to do was to photocopy that and see if they could see the different carbon chemistry between the toner and the paper. So this is a carbon image of the photocopy. And what they did was they added up the spectra in this region here, which would be the paper, and then a region over here, which would correspond to their symbol on the toner to give you a better signal to noise. Then look for those line shapes at each particular pixel in your image. And when they do that, these are the results you get. So this is one component. It shows you essentially that phi symbol. And down here, the other component, which shows you the paper. So this is the toner, and this is the paper. So you separate out the different carbon chemistries in this particular map by looking at the different line shapes of carbon at basically each pixel, how much of each line shape is present at each pixel. This is an example of wear on a camshaft globe. And I think you just go ahead and read this yourselves later. Okay, talks about the different components that they've found. These are different images. This is zinc, so forth. And you can see the different places where these elements are present. Wear tracks, analyzing wear tracks, also a useful application in XPS, and looking at the different compositions in wear tracks, showing you, for example, here, iron in green and molybdenum in red. So this is molybdenum disulfide and in the wear track. I mentioned about these new instruments that work at higher pressures than the ultra-high vacuum and the so-called near ambient pressure XPS instruments. I just want to draw your attention to those, that these are now commercially available and we can operate at more of an environment, particularly in the biological field, to analyze materials. And but electrons don't travel very far when you don't have ultra-high vacuum. And for example, the electron mean-free path is about 4 millimeters at 1 bar for a 400 eV electron, okay, in oxygen. So we don't have much distance where electrons can travel after they come out of a sample if we're operating a system at these kinds of pressures. So we have to have the sample placed very close to an input aperture in the instrument. So the electrons have a high probability of getting into our analyzer before they're being scattered by the gases that are present. So these instruments are typically going to have multiple pumping stages and apertures between the different parts in the analyzer and compared to the analysis chamber. So they're quite complicated. They're going to have multiple pumps, typically turbomolecular pumps, between these different stages. So we go from a fairly reasonably high pressure to ultra high vacuum into when we get to the hemispherical analyzer. This is just an image showing you typical one of these near atmospheric pressure instruments. The different stages, as I mentioned, there's a small aperture here, and the electrons come off a sample which is placed very close to this aperture. They go into this first region, which has its own pump. They go through another aperture, another region with its own pump, another region with its own pump, and then into the hemispherical analyzer to obtain a spectrum. So you can analyze liquids with these particular type XPS instruments. And this just shows you an example down here of one of these types of analyses using these near atmospheric pressure XPS instruments. I also mentioned the Auger parameter, and the Auger parameter is very useful when we don't have a chemical shift in a photoelectron peak. I mentioned barium. Barium doesn't shift very much in terms of different chemistries. But the Auger parameter was defined as the energy difference between the photoelectron peaks and an Auger peak. So that energy difference is the Auger parameter. And that energy difference that we have is very useful for understanding different chemistries, because the Auger peak shifts more than the photoelectron peak. So in the case of barium, the photoelectron peak doesn't shift significantly, but the Auger peak does. So by measuring that difference, we can tell what the chemistry is, but also we need to use our spectrum if we have oxygen present and so forth as to what the compound is. So the Auger parameter is very useful. And by adding on the X-ray energy to what we measure, we get a number that's always positive and independent of the X-ray energy used. Remember, when we change our X-ray energy, the Auger peak shifts in the spectrum. So the Auger parameter will be different when we use different X-ray sources. So by adding in the energy of the X-ray source, it cancels out that problem and we get one number. And we call that the modified Auger parameter rather than just the Auger parameter. So modified Auger parameters are what we normally use and are very useful, okay, for doing this chemistry analysis. So we measure the energy difference between, this is a case of molecular sieve, between a silicon photoelectron peak and a silicon Auger peak here. And this is the silicon Auger parameter. Then by adding on the X-ray source energy, we get the modified Auger parameter. So that's how we measure these, and we use that to understand our chemistry. And here's a plot. This is a plot from sodium, and we can generate these plots ourselves. These Auger parameter plots is also called a Wagner plot, because Charles Wagner also was basically the first person that talked about these Auger parameters. And there's a database, NIST XPS database number 20. It's free and it's online. And here's the link to this database. So using this database, you can generate a chart of the modified Auger parameters for different compounds of different materials. So this is for sodium. I'll show you this as an example. This is pure sodium. This is up the top. And these are different compounds of sodium. And the Auger parameter plots, the binding energy is plotted on the x-axis, and the kinetic energy of the Auger electron is plotted on the vertical axis. So the Auger parameter is determined by the sum of the binding energy and the kinetic energy. And these are the numbers over here. And you can see in sodium, different compounds, the binding energy is not changing significantly at all. The binding energies are all much the same. But the kinetic energy of the Auger peaks is changing significantly. Here's the metal, and down here, different compounds. So the difference between the energies of the photoelectron peaks and the Auger peaks are changing a lot and can be very useful. So sodium, the photoelectron peak doesn't shift very much, but the Auger peak does. So the modified Auger parameter can be extremely useful. So you can generate these. So if you're studying barium, you can generate this from the online database and generate your own Auger parameter plot. So you can do this for many, many elements and have your own plot, which can be very useful to help you understand the chemistries. But don't forget, you'll also have the peaks from the other elements present as well. So you have to use all the information you can and all the tools you can access to get the best analysis in your spectrum. So you need all these kinds of things. Sometimes you're going to need one more than the other and so forth. But you need to know about all these so you can apply them all to get the correct analysis. Sorry, I'm sort of rushing through here. I'm trying to finish at a reasonable time. We started a bit late, but you have these copies of the slides, and you can always go back or email me or talk to me tomorrow between breaks if you have more details and questions on these particular aspects. But like I said, there's a lot of things in XPS, and I can only cover certain things. This is gives you the calibration for the spectrometers for magnesium and aluminum X-ray sources. So if you want to calibrate your instruments, this is an ISO standard for calibration of instruments. And the instruments are very stable, and they recommend that you check your calibration of your energy axis every 6 months in your instrument, unless you change something in the meantime. If a power supply goes out and you use another one or something, you need to recalibrate your instrument. Similar to Auger spectroscopy, we use sensitivity factors. We measure the peak areas in XPS and compare them with the peak areas from the pure elements for that same transition. And just like in Auger spectroscopy, we have this formula. The fractional composition is the measured signal divided by the sensitivity factor. And again, we sum this, so the sum of all the concentrations will come up to 1. So you pick one peak for each element and divide that area by the sensitivity factor to get the quantitative analysis. This is a table of sensitivity factors from physical electronics, and this is what a lot of their instruments still use, and these are not really reliable because they were obtained from different compounds many years ago, and they made corrections for different parameters and so forth to come up with these sensitivity factors. But the main thing, again, I want to point out is how the sensitivity factors vary between the different elements. Lithium has a very low sensitivity factor, 0.012, compared to fluorine. Fluorine's placed at 1, and everything is compared to fluorine. So lithium fluoride, the spectrum of lithium fluoride, the area of the peak of lithium is going to be almost 100 the peak area of fluorine. Big difference. So the lithium peak is very small compared to the fluorine peak. Again, you just don't want to say you have a small amount of lithium because the peak is small, because the sensitivity factor is small. So you must correct for the intensity of a peak from a certain element in its pure state and compare them with some element. And these are all here in this particular table compared with fluorine being 1. And again, you can see the sensitivity factors vary by a factor of 100 between the different elements. So for the light elements, you can only use the 1s peaks. And as you go to a higher atomic number, you're going to use different shells to do your quantitative analysis. And you'll notice here in this particular table, let's say 2p, and this is sensitivity factor for 2p, because these peaks are very close together and maybe not resolved. Then later, for a higher atomic number, these peaks are resolved, and they're only using one of the doublet peaks. So here's 2p 3/2. So you must make sure you're using the correct sensitivity factor. If you're using a doublet peak, or if you're using just one of the doublets to do your quantitative analysis. And here are reference spectra of copper, silver, and gold in XPS, also developed from the National Physical Lab in the UK. And again, these should be also included in all instruments that are sold. So we have access to compare our instruments with these reference spectra to see how our instrument performs compared to somebody else's. But again, unfortunately, it's not done. And again, this is over 30 years old. Detection limits. Detection limit depends upon the sensitivity factor, the signal to noise ratio in the spectrum, which is determined by the X-ray flux, the energy resolution of the analyzer, aperture settings were available in different instruments, and the time to acquire the data. So all these things come into play to determine the signal to noise and the detection limit. You might also have peak overlap problems. And remember, I mentioned that maybe you can change the X-ray source to get rid of an overlap problem. But the detection limit is very similar to Auger spectroscopy. About 0.1 to 1 atomic percent is a typical range of detection limits in XPS. You can spend more time looking for a certain element that will improve the detection limit, okay? But in a general number, 0.1 to 1 atomic percent is a reasonable detection limit in XPS. I want to show you an example about adhesion. This is a spectrum that was taken by a colleague, and it was on an aluminum bond case. The aluminum bond failed, and he was trying to determine if the bonding failed at the interface with a primer. And the primer used is a chromate-based primer. So he was looking for a chromium peak. And I just happened to walk by when he was doing his analysis and said, you know, when you finish your analysis, let me know, please, because I would like to use the instrument, because we shared a lot of instruments. And he said, oh, I'm done. I said, oh, okay. And this kind of a spectrum was showing up on the screen. And I said, what were you trying to do? He says, well, I'm looking for a failure mechanism for adhesive bond, and I'm looking for chromium, and I don't detect chromium. Therefore, I know it wasn't a problem with the chromate primer. So the bond didn't fail in the primer. And I said to him, do you think you have enough signal to noise? And he said, yes, I do. Because chromium is going to appear here. It's going to be a doublet peak. And if it's a chromate primer, he thought that he would expect to see a large chromium peak if it's a failure mechanism in a chromate primer. I said to him, well, you know what? In aluminum, turns out you have a very low chromium concentration at the surface of the primer. And I said, I've done a lot of work on primers, on aluminum alloys, and I know you don't have enough signal to noise really to say that you don't have that failure in that primer. And he says, oh, no, I'm right. I don't need your advice. I'm quite happy. There's no failure mechanism in that primer. Well, I wouldn't want to fly in his planes that use that particular bonding. Here's some spectra I had from my database. I have an enormous amount of spectra from different primers and so forth on different alloys. And these are two spectra I'm just showing you here for comparison. And one of these has a chromate primer and one does not. And if you take a quick look at them, there are some small differences between the spectra. Like this one has a sodium peak, and but chromium's here. If you don't look very carefully, you'd miss the fact that one of them has chromium on it. Because as I mentioned, the chromate primer at the surface of the primer has a very low signal from chromium, very low signal. And so these are reference spectra. And if I blow up this region here in between and compare them with oxygen, this is an oxygen peak. This is the oxygen peak. And you can see one of them has this doublet from chromium and the other does not. And this is the spectrum from a chromate primer. And based on atomic percent, only 0.3 atomic percent chromium is detected at the surface of the primer. Because the mechanism people believe in the chromate primer is that the chromium diffuses towards the aluminum and improves that adhesion and the bond. And he did not have this signal to noise to say that there was no chromium present. But he didn't want to know, he wasn't interested, but I knew that he did not really have enough signal to noise because he didn't have a reference material. He never put a primated sample in to see what signal he would get from a reference. He just assumed it would be a big peak, as you might expect if you have a chromate, but it wasn't the big peak in that particular case, but he wasn't interested. So you can't teach PhDs, okay? You can't suggest to them to change their method. It's already ingrained in them. Another example, a PhD who shares the equipment, a different person. Once I told him, I don't think you're operating the machine properly. Well, he was not appreciative of that. And I said, you need to change your pass energy in your survey scans. He did not use a high pass energy. He used a small pass energy because a small pass energy is going to give you a better resolution. But the counts are much lower. And I said, why don't you try using the highest pass energy in the instrument? And he didn't even want to take a couple of hours to try all different pass energies on a sample and compare them. He just believed that if you take the best resolution you can get in the machine, you're going to get the best result. You know, you can't convince PhDs, in many cases, to change things. And I was not making him change it. I wanted him to do a study to see that, yes, he could improve his method for acquisition by changing some parameters. And in an hour, he could take all these spectra and compare them. But this is a common problem in XPS analysis. People use wrong combinations of pass energies and so forth. I showed you that example, 2 hours for that survey scan versus 5 minutes. People don't take time to change a parameter and see if they can improve the way they're taking data. So if you're going to use XPS in a project, you want to take data different ways and see how your machine's working and understand your machine and know what you should use to answer your problems, to do your research. Okay. I just an example here, of peak identification. Okay, and these are just portions of an Auger scan. I took survey scans, but I'm just showing you a portion of the survey scans. This is the low binding energy range, 0 to 300. And the peak going off the axis here is carbon. This is carbon. So here's the result that was obtained using the software. And I didn't include these two peaks. These are silicon. These two relatively large peaks are silicon. So I didn't label them here, but the software said this is phosphorus. And it labeled this peak here as chlorine. one over here is chlorine. Well, if it's phosphorus, phosphorus has to have another peak here, where I've got the dashed line. And the intensity is going to be similar to this one. Well, there's no indication of a peak there, so it can't be phosphorus. So the software misidentified the peak. It's not phosphorus, it's something else. So you have to look for other possible elements that might be present in this particular energy region. And one of them is strontium. It turns out that this peak is strontium. And when you identify this as strontium, it turns out strontium also has other peaks. It has one over here. And also, this chlorine peak has wrong intensity. This chlorine peak should not be bigger than this chlorine peak. Yet it is. So I know that something is overlapping with this peak here of chlorine. And it turns out it is a strontium peak that's making that peak bigger. And there's also a strontium peak right here near the start of the carbon peak. So it's definitely strontium. And if you really want to confirm it even more, you could take this at better energy resolution, and then you can see that the peak is actually a doublet with the right intensities, confirming it's strontium. So again, you must be careful with the software identifying the elements. There's an example of the wrong element identified, and also the wrong relative intensities of the chlorine peaks. A lot of you are working on fibers or nanoparticles. I just want to mention that if you're calculating overlayer thickness on a curved surface, you must be very careful. You can't use the software that comes with the machines that assumes that the sample is flat. The calculations for analysis, for quantitative analysis, assumes that the sample is homogeneous. So if you have spherical particles, for example, you're not going to get the right composition if the particles are spheres. So if you use the software that comes with the machine, you're always going to overestimate the thickness of your films on your curved surface. And there's a reference here to this paper that describes in detail this. And I also want to point out that there's a free software package called XPS Multiquant that was developed by my colleagues in Hungary. It's free, and it's basically software they wrote for curved surfaces, fibers, spherical particles, and so forth, for working out thicknesses of different layers on curved surfaces. So if you're working on nanoparticles, you might be interested in this software that you can download for free. It's called XPS Multiquant. And they're up to a high number now. I'm not sure what the latest version is. And they also give you a manual for free as well. You can also simulate spectra if you're working on curved surfaces or fibers by using this software. The simulation of electron spectra for surface analysis called CESA, version 2.2 from this particular link here from the NIST standard reference database. And luckily, it's nice now because it's free. When I got my first copy, version 1, I had to pay $1,000 for it. But a lot of people complain because this is a government agency, and it was developed by university people, and NIST was sort of distributing it. And people complained and said they shouldn't be selling this. It was developed by somebody else. So eventually they decided, yes, they should give it away. So they got version 2.2 now, and it's free. So you can simulate Auger spectra on flat surfaces, spheres on flat surfaces, all kinds of different things using this free software from this NIST database 100. Hey. let's see. And X-ray damage. This is a plot from the at high resolution XPS of polymer database showing you possible beam damage. This is time, oxygen containing polymers and chlorine containing polymers, how the oxygen and chlorine can change with time in doing your analysis. Okay. Well, guess what? A few more slides. We'll try to finish up. I showed you this earlier about the charging of the sample. And you can still do quantitative analysis. If I shift the peaks to the correct energies, the silicon dioxide, you can see the result comes out very close to silicon dioxide, even though the peaks are very broad from charging. This is a case where people misidentified the spectra on silver. These were silver nanoparticles also on silver. And they interpreted this spectrum to be a combination of two different silver chemical states. Metallic peaks shown here in green, and some chemically shifted silver peaks shown here with the purple markers. Okay. Well, when I saw their report, I said to them, that's wrong, because silver doesn't shift very much. It definitely can't shift by, like this is about almost 5 electron volts. It just can't do it. It's impossible. And this is a case of charging. Some of the spherical particles charged. So these purple indicated peaks are silver, but those particles charged, and the peaks of silver from those particles shifted. So they've got the silver that doesn't charge in green, and the silver that's charged in purple. Okay, so it's not a chemical shift, it's just that the signal from the particles charged and shifted in the spectrum. Because silver, as I said, does not shift by 4 electron volts for any kind of chemistry you have. And you can subtract off, for example, a reference spectrum of silver from that and see what's left over and get an idea of how much you have for that particular shifted peak from the particles. Here's an example also of shifts in a depth profile where the carbon peaks are changing due to charging during a sputter depth profile. In the software, we can align all these peaks to be at a fixed value for carbon, and also it will adjust all the other peaks in a sputter depth profile for you. So here is the example, and here are the corrected peaks that have all been shifted basically to the same binding energy. So data processing, lots of different things that we can do as well in data processing, just like in OJ spectroscopy. And depends on your software. Satellite subtraction, we can remove satellites. In the case of magnesium spectra, we have these satellites, we can remove those in the software. We can also measure peak areas, we can measure peak energies and things like that in the software. We can also put tables of concentrations in our plots. We identify the peaks in a spectrum. We can do curve fitting, okay, in the spectra, different ways for doing that. Okay. And I think this is probably a good place to finish. I think I started an hour ago. So this is a good place to finish. I'm sorry, I'm sort of rushing this a little bit towards the end, but I wanted to try to catch up with our schedule somewhat. So tomorrow morning, we have one more session for an hour and a half on XPS. And tomorrow we're going to start off with the curve fitting. So curve fitting is something a lot of people do in XPS. So I'm going to take more time with the curve fitting. So this is a very good place to finish today, and we'll continue on here tomorrow. So again, I apologize for rushing through somewhat with some of these slides, but I want to show you as much as I can in the time that we have available to talk about these different aspects of XPS. Okay, so thank you.
Thank you very much, sir.
Okay.
So now our next speaker is Dr. Shahzad Alam. His area of expertise are nanocomposite coatings, biocompatible implants, and smart materials. I will not take more time, so I will request Dr. Shahzad Alam to come, please.
Bismillahirrahmanirrahim. Start with the name of God, most merciful and the beneficent. First of all, I like to express my sincere thanks to the organizer for providing me this opportunity to make this presentation. I'm also thankful for their warm hospitality. I can imagine, Prof, you must be exhausted. Series of lectures, then the traveling, and I'm quite sure that as far as this presentation is concerned, it will be a pleasant break for you. You can enjoy a good hot coffee meanwhile. Well, ladies and gentlemen, since we are all talking about the vacuum and the vacuum application, especially on the surface science, so I'll be talking about the nanocomposite coatings produced by a lateral arc rotation cathode, we call it LARC, and the opportunities and the challenges. Since I have been working for PCSIR for more than 35 years, and the basic idea of this organization is to help the local industry. We help them in terms of quality control, quality insurance, troubleshootings, testing, and this kind of a thing. So as far as my talk is concerned, I'll be talking about the applied side of these nanocomposites and their engineering application. Well, before I proceed further, I like to share with you the format of my talk. First, I like to talk about the importance of vacuum technology to synthesize nanocomposite coating. If you really want to synthesize a good quality coating, it is very important to have a good adhesion with the substrate with the minimum level of imperfection. So I'm quite confident that as far as the vacuum is concerned, vacuum plays a very important role to control these imperfections. Second thing is the surface modification by PVD coating techniques, and then the improved form of the PVD, we call it LARC, lateral arc rotation cathode PVD coating techniques, the comparison of characteristics of the arc and the LARC technology. Then I'll be discussing the industrial coating produced by this LARC technology, the nanocomposite coating, the characterization, and finally the concluding remarks. Well, I think I can, since they said I have only 30 minutes, 35 minutes, so I can skip a few of, these, well, as far as this coating is concerned, PVD is concerned, we can divide this method into two. The one is the PVD coating, the second type of very important industry coating, we call them CVD coatings. And both of which requires a high level of vacuum to create a clean and controlled environment for coating deposition. By achieving low pressure, manufacturers can eliminate the impurities and ensure uniform coating thickness. So this is something very important. As far as the adhesion is concerned, vacuum technology assists in improving the adhesion of the nanocomposite coating to the substrate. And during the vacuum deposition process, the substrate is typically clean and prepared through techniques like we can use ion sputtering or the plasma treatment. These two methods help improve and remove any contamination or the oxide layer from the substrate surface, allowing for better adhesion of the nanocomposite or other kind of coating. Now I'd like to talk about the surface modification. What is this surface modification? Well, the surface modification is a valuable technique in order to produce the desired properties on the top of the surface, irrespective of its internal or the base material or the substrate. And in the industry, using the different kinds of surface modification techniques like electrolysis plating, CVD, we call it chemical vapor deposition technique, PVD, physical vapor deposition, plasma coating, which is again a very, very important coating technique, cladding, anodization, bluing, and the thermal barrier coating like zirconia and yttrium. These kind of a coating, we use it for a high temperature application, and the pack cementation. So these are the different kinds of surface modification techniques which the industry is using depending upon their requirement or the nature of the application. So as far as my talk is concerned, I like to just focus on the PVD technique right now. What is this PVD? It's a physical vapor deposition technique. Well, it is a vacuum deposition technique and is a general term used to describe any of a variety of method to deposit thin films by the condensation of a vaporized form of the material onto the surface, for example, on a steel substrate. And different types of the PVD, which includes a vacuum deposition, sputtering, another type of PVD, arc vapor, another type of PVD technique. And then there is a very improved kind of, the latest version of PVD, we call it LARC. It means that is a lateral arc rotation cathode technology, and we call it LARC thing. And then the ion plating or ion beam assisted deposition techniques. So these are the different types of the PVD techniques which are in practice in the industry. And as far as the nature of the PVD, this kind of a coating is concerned, we can produce these coatings either single layer, double layer, gradient, multi-layer, or the composite. I just give you example. This is a substrate, and here we have a single layer coating. Here we have a substrate and the double layer coating. You can see these two coatings. Then we have the gradient. Substrate is here, and the composition is changing from the substrate to the top of the surface. Similarly, we can also produce the multi-layers. You can see these substrate is here, and you can produce the thin layers of these coatings. And finally, the composite type. So these are the different kinds of coatings which you can produce with the help of this LARC technology, depending upon their, the application. In the PVD technique, the coating method involves purely the physical processes, such as high temperature vacuum evaporation or plasma sputter bombardment. rather than an involving a chemical reaction at the surface to be coated. What we need for the PVD coating? We need an anode. It means the part which is to be coated. We call it substrate. Then we have a cathode. What cathode is? Cathode is the material to be coated. For example, titanium in the titanium nitride coating. Then we need a plasma creation. And for that purpose, we normally use argon in that chamber. Then we need a reactive gas. And normally we use nitrogen in most of the cases. And the deposition of the coating on the substrate. So these are the prerequisites for the PVD coating, that you need a anode, cathode, plasma, reactive gas. Well, as far as the PVD right now is concerned, I already have explained it that generally the industry is using the arc deposition technique, and the second is the log technique. I like to discuss with you, what is this arc and then the log, and then give you the comparison of the characteristics of the both technique, and like to tell you, which one is better and better for the, different kind of high-tech applications. First is the arc technology. In the arc technology, cathodes are, the deposition is a physical vapor deposition in which an electric arc is used to vaporize the material from a cathodic target. The vaporized material then condenses on the substrate, forming a thin film. This is a schematic view. I hope that I can explain in a better way right now. This is a chamber we have. This is a substrate. Already I've explained this is a substrate is anode. We have a cathode here, and the plasma is generated here in this chamber. For that purpose, we use argon, and the vacuum chamber that's a substrate. And one thing which is noted here, that in the arc technology, the cathode is fixed. Cathode is not moving at all. But in the arc technology, this is advanced technology in PVD coating. Both water-cooled cathodes are in permanent rotation. In the arc technology, the cathodes, they are not moving at all. They are fixed. But in the log technology, the cathodes, both cathodes, they are moving along their axis. And the most important advantage of the log technology comes from the rotating cathodes and their lateral positions. If you use this technology, you can have very promising properties of these thin coatings, which I like to discuss with you right now. This is our PVD coating center. We developed this center at PCSIR Lahore, and this is a Swiss company platted 580 unit. Schematic view of the PVD coating log technology. You have these two cathodes, which they are, and those cathodes, they are moving, and these are the series of the substrate, which are again moving. Another close view of the principles of the log technology. You can see these are the two cathodes, and these are the samples which are supposed to be coated. And you can see it from here. It's a titanium nitride coating. What are the drawbacks? As far as the drawbacks of the arc technology is concerned, the cathode remains stationary during the coating process. Vaporized material is used insufficiently. Film deposition properties are suboptimal, and this technique produces the big micro droplets, which diminishes the surface quality of the coating or the tool. If you use the arc technology, it means that the quality of the coating is not that good. It gives the droplets, the surface is not very uniform. It's not very, some of the micro porosity or micro holes are available as far as the top of the surface in the arc technology. Whereas in log technology, both cathodes and the fixers, they are in permanent rotation during the coating cycle, providing uniform coating. A very good surface coverage, you can have it, and the vaporized material is used very efficiently. Very good surface finish at the end of the day you achieve. In fact, the session after the lunch is always very bad, Prof. After having a, heavy lunch, most of the people are, sleeping or feel like sleeping. So भाई थोड़ी देर और बर्दाश्त कर लो जब थक जाओ तो मुझे बता देना है This is a comparison of LARC and the ARC technology. Okay? You can see this is ARC surface profile. We have measured this surface topographical analysis by the atomic force microscope and just compare the both surfaces. This is LARC, this is ARC. You can see the droplets, like these are the droplets, metal droplets. If you can experience some metal droplets on the surface of a coating, you don't like it. You said, no, I don't want that. Plus, you can see the micro voids, micro porosity, and some of these voids are quite, big as well. When you compare this structure with this, you can see it's a very dense structure. And microstructural imperfections, they are at a minimum level. There is no micro metal droplet here. And the porosity and the micro porosity or the voids, they are at a minimum level. And this is a surface roughness. And in large technology, the surface roughness is 0.072 to 0.15 micron. Whereas in the ARC technology, the surface roughness is 0.2 to 0.45 micron. So difference is there. So what sort of different kinds of coating we are producing? In fact, in our center, we are producing about 12 different kinds of these coating. Some of these coatings are of a very basic nature. Some of them are very special, and some of them are really breakthrough coatings. I'd like to discuss with you, these coatings and their engineering application. Like this titanium nitride. This is a golden color coating, and we use this kind of a coating for the cutting, forming, injection molding, and tribological application. When we say tribology, it means that a coating which has low friction, high wear resistance. We call it good performance tribological coating. And as far as the harness is concerned, for this coating, the harness is about 24 gigapascal. Right, G? Coating thickness is 1 to 7 micron. Coefficient of friction is about 0.55, and the maximum usage temperature is around 600 centigrade. You can use this coating at around 600. This is, as far as the titanium is concerned, it's a very basic kind of a coating. Chamber view, you can see these are the different kinds of drill machines, different size, and here is a cathode which is moving. Another view of the series of different kinds of drills, which we have produced for the CNC machines. The hardness, thickness, and the coefficient of friction is more or less the same. This is a cutter for tobacco industry, another cutter for the tobacco industry. Since Pakistan, Prof, is exporting the surgical instruments to the different parts of the world, and our export is around $300 US. And we are producing the best quality surgical instruments. And, sometimes the value addition is a big thing. People were exporting from here to Germany, and the Germany is putting their own stamp, and they apply this kind of a coating, and they re-export or with their name. So at the end of the day, to be honest, we were just having, a small check of the that kind of a thing. So what we did that we helped the local industry, the surgical industry in Sialkot. We applied this kind of a coating. These coatings are biocompatible. They increase the hardness, they increase the wear resistance with a low coefficient of friction. Plus, they increase the service life of the Caesar and the value addition. Like they were selling these Caesar for about $1. With this kind of a coating, the same Caesar can be sold out, for about maybe 10 or 11 or $15. So at the end of the day, the industry is really having a good profit. Similarly, these are the different kinds of titanium nitride coatings, which we have applied for different kinds of industrial application. Since the time is too short, so I don't want to go into the detail. These are the cutting tips. Well, as far as the bioimplants are concerned, generally, titanium is the right material for bioimplants. But in Pakistan, to be honest, because of our socioeconomics limitations, generally, most of the people, they can't afford to have the titanium. So second choice is 316L. 316L is another surgical, the material which can be used for these kind of implants. But unfortunately, even the 316L is not in practice. People are using the nitronic. What happened is just because of the carbon secretions, you have to chop the leg or the arm of that poor fellow because of gangrene. That was a serious problem. So Alhamdulillah, my team, one of my colleagues is sitting here. I was so happy to see him here. They develop all these kinds of different kinds of these coating. And Prof, we applied those coating on these bioimplants and help the, the poor people. Instead of buying about 2 lakh something titanium implant, you can have the same implant for about 35,000, less than 35,000. The only difference is, since the titanium is light material, high strength light material, but this is 316L with the biocompatible coating, the density is slightly higher. That's the only difference. Otherwise, rest is same. G? Life is the same, G, like titanium implant. Life, are you talking about the life of the implant? Sir, forever. Jab tak aap zinda hain. Allah mi aapko zindagi de. Another very important thing is these, hip joint. This was again a very, very important area. And generally we use with nitronic 30 material. Not very good material. It's not clean. A lot of impurities, a lot of imperfections were there. So the team applied this biocompatible titanium nitride coating. And then there is another version of these hip joint. We applied here the hydroxylepatite. Ali sitting here, he's a man who did this job. We applied hydroxylepatite, Prof, on this stem. Once you apply the hydroxylepatite, what happened is you implant this hip joint here. With the passage of time, what happened? There is because of the osseointegration, that hip joint becomes a part of your original bone, and it won't hurt you. That was, Alhamdulillah, that was a big thing, and people are still working. I think the clinical trials have been completed. I'm not sure. Still going? Because I'm retired now, geez, it's almost 4 years now. My team, they are working on it. So this is again a very, very, very important area which really helped the poor people. In addition to that, we were exporting these dental tools like scalers and different kind of thing to the Germany. And the Germany was applying these, the titanium nitride coating, the golden color coating on the tip of those scalers. And they were really enjoying a very good profit out of it. So what we did, we really helped the local surgical industry. We applied these all titanium nitride or the nano coatings on the tip of these, these dental tools, and that increases its life, reduces friction, and increases its wear resistance and the biocompatibility as well. In Pakistan, you might have seen, many dentists, they are sitting along the road doing the operations and without any, hygienic conditions. So that was a serious issue. So with these kind of coating, you just clean it with the help of alcohol, and it is much better, and it's a biocompatible. Another type of coating, we call it titanium carbonate coating. We can use these kind of a coating for milling and tapping, stamping, punching. The hardness is about nano hardness. The gigapascal is about 37. Thickness is 1 to 4 micron. And the coefficient of friction is about 0.2. And we can, the maximum usage temperature is 400 degrees. Titanium aluminum nitride. This is again another kind of a very, very good coating. And these are its practical industrial usage, and these are its technical data. The hardness is about 35 gigapascal, and 1 to 4 is the, micron is the thickness. I think I can skip a couple of them. Another very good example is this DLC. We call it diamond-like carbon coatings. In the textile industry, we use these kind of pattern for making different kinds of pattern in the industry. And for that purpose, we need a very good friction, low friction, high wear resistance. This is something very important because the yarn has to, move on this coating at a very, very high speed. If we use a simple steel within a very short time, it will be, it will worn out. But this kind of a coating, they increases its life maybe 200 times or 300 times. And these coatings were diamond-like carbon coating, and these coatings are self-lubricating diamond-like carbon coating. The hardness is about 20 gigapascal. The thickness is 0.5 to 4 micron. Imagine 0.5 micron coating. And the coefficient of friction is about 0.15, which is really very low coefficient friction. This is a micro titanium nitride coating and titanium MP coating, chromium nitride coating. And this is even for zirconium nitride. Zirconium nitride is a very, very high-tech coating. Pakistan ke liye bahut mushkil hai jisko lena aur karna. But we have a cathode to produce these kind of a coating, our center. This was micro bearings. We applied these nano composite coating on these bearings. Another mold drive shaft. I'd like to spend a couple of minutes just for the nano composite coatings. Well, as far as the nano composite coatings, they refer to a type of coating that incorporates nanoscale particles into a composite material, enhancing its properties and performance. These coatings typically consist of a matrix material combined with the nanoparticle, which can be metallic, ceramics, or organic in nature. The nanoparticles are typically dispersed within the matrix and the nanoscale level, resulting in a homogeneous and highly functional coatings. And one of the main advantages of the nanocomposite coating is their ability to provide improved mechanical properties, chemical properties, and thermal properties compared to the conventional coating. If you apply this kind of a coating, you can enhance its mechanical, chemical, and thermal properties. The incorporation of the nanoparticles can enhance hardness, scratch resistance, wear resistance, and corrosion resistance on the top of the other properties as well. Well, as far as the production or the synthesis of the nano composite coating with the help of lath technology, if we produce these coating with the help of lath, it gives you the extremely important for the dry high performance cutting. It is very, very important that if you want to go for the dry high performance cutting, these coating can be useful. And if the further improvement is possible, if the nanocomposite is deposited with the nanolayer basic structure. To achieve this structure, it is essential to build the cathodes close to each other. This is a kind of a trick which I'm sharing with you, that if you want to have a very good quality, since the cathodes they are moving, you have to bring the both cathodes close to each other and close to the substrate, and you can have a very good quality coating. In this coating, the hardness you can have is about 40 to 50 gigapascal, and the coating thickness, I think I can skip this one as well. So how much time? 5 more minutes. Well, as for this is a nanocomposite structure. You can see it from here. This is aluminum nitride, the particles, nanoparticles, which are embedded in the matrix, and the matrix is silicon nitride. The particle size is 3 nanometer for these nano particle. The nanostructures. As far as the nanostructures are concerned, for the nanogradient, the layer is about 3 to 10 nanometers, and the nanocomposites, nanocrystalline grains are embedded in the amorphous matrix. This is a TM nanostructure of the nanogradient coating. You can see it here that as far as the composition is concerned, it is shaded. These are the gradients starting from here to here, aluminum. Then we have, these are the nanolayers. You can see these nanolayers. Then we have the nanocomposites. These are the nano composite coating. And you can see it here that the the harness is about 45 gigapascal and the thickness is 1 to 4 micron. And the coefficient of friction is about 0.45. And the usage temperature is about 1100 centigrade. This is another type of nano composite coating. And this is a comparison of surfaces. I can skip this one, skip this one. Sometimes it is very difficult and you have to finish everything in 3 to 4 minutes. It's difficult which one you like to choose and which one you like to leave. Well, as far as the characterization is concerned, I think Prof is already discussing with you different kinds of characterization techniques. And he has discussed in depth those techniques. I'm sure those will be very, very useful. And those informations are really valuable. And I'm sure that will be helpful for you for doing somebody's doing the the PhD or some research work. Those things are very, very valuable. Kindly make your own notes as well. And at the end of the day, I'm sure you'll see the difference. But for, the characterization of these nano composite coatings, we normally use atomic force microscope first to study its topographical analysis. And then we use for measuring the mechanical properties, which includes the nano hardness. And for that purpose, we use a nano hardness tester. Generally, the hardness is measured by the Rockwell, Vickers, or the Brenner. But in this case, coating thickness is 1 to 4 or 5 or 3 micron. It's very, very thin. For that purpose, you can't use the ordinary, the hardness tester. For that purpose, you need a very, very specific nano hardness tester. And if you want to measure the adhesion of the coating, for that purpose, you will use the micro scratch testing. And for tribology, study the friction and wear. You will use a pin or ball on disc trivometer. And for measuring the coating thickness, there's an instrument we call it calotest. And finally, the microstructure is studied by the scanning electron microscope. I won't go into the details. This is atomic force microscope. That's the principle, how it works. Since I have only maybe 1 minute. So that's the principle of the microscope. I won't discuss this. This is a nano hardness tester. And this nano inventor gives you the indentation hardness, elastic modulus, and the creep. And it is good for the research development and the quality control. Micro scratch testing. With the help of this testing, you can have measure the coating adhesion, scratch resistance, and the viscoelastic recovery. This is a schematic view of these scratch tester. For the tribology, and we will measure the coefficient of friction, wear rate, and the lifetime. This is a trivometer. For the measuring the the thickness, we'll use this calotest. You can see it from here. For the multi-layers, I'm not going to discuss. I love to discuss this calotest. It's a very, very unique test, but since the time is too short, so we can use even after this lecture, if somebody is interested to know the details about these factorization techniques, we can discuss. Let me conclude my talk with these words, that as far as the practical or the industrial application of these coating is concerned, there is a huge application. We can use this coating for the industrial development, self-reliance, saving a lot of foreign exchange, for auto industry, for surgical industry, for petrochemical industry, for aerospace industry, for automotive industry. There is a huge potential of these kind of coating. And with these words, I'm sorry that I have to rush. My sincere apology. And with these words, once again, thank you very much to the organizers, sir. Thanks to you and to the dear audience for your patience. Thank you. If you have any questions, we can always discuss. Please. I have one of my slide, give you the comparison, the topographical analysis of the both services. One is the ARC technology, and the second was, the coating which was produced by the large technology. And the surface roughness, there was a huge difference. In the ordinary coating, there was droplets, metal droplets, voids, microporosity, and the surface roughness was rough. RA value was pretty high. But as compared to that, with the large technology, the surface finish was very homogeneous. It was excellent surface finish, and with the minimum level of microporosity and the void. Would you like to see?
I think this simple sputtering system, if we use, we can attain the average roughness maybe in few nanometers. I think if I compare the parameter of roughness, then that sputtering system should be much efficient than the large technology.
Well, I think that large technology is much efficient as compared to the ARC technology. And I have given you the results of the atomic force microscope, and the results of the topological testing, the results of, even the scanning electron microscope. All those results, they shows, the very homogeneous, a very good surface finish of the ARC technology. Why it is so? Because the cathodes in the ARC technologies, they are moving, and their lateral position gives you a very uniform, the structure. Plus, you can control the recipe as well. If you want, in the ordinary, ARC technology, you cannot change the recipe, and there is no, control for the changing the recipe. But in the ARC technology, you can change the recipe, changing the, composition of the
We
whole.
can change parameters to get
Cheap.
another technique.
Exact.
And as far as the uniformity is concerned, since your objects are cylindrical, but the coating stays on the top of the cylindrical object, so how you maintain the uniformity of cylindrical objects?
Good question. Since in the chamber, you have, vapors everywhere. And those vapors, they condense on the material, whether it is on the top, on the side, even at the bottom. There's no problem.
Thank you very much, sir.
Do you
Very
want
nice
to
talk
use-
on art deposition. So according to your program, maybe we have to finish, but we will take like 20 more minutes. So another very short brief talk on the PVD. So on a lighter note, I will sell my own product. I say I have a better options later than the lateral, I mean the art deposition. So I will very briefly talk about another PVD coating techniques that are the sputtering. Will be very brief. Maybe I will skip few things already discussed. So my name is Muhammad Arif, you already know, so I will very briefly talk about and other coating techniques. And at the same time, we have developed a kind of in situ surface assessment techniques for the sputtering target. So I will also discuss the same in addition to the PVD coatings. There are the contents. I will slightly brief about the coating technologies, PVDs, and thermal evaporation, which is also types of PVD, and finally sputtering, reactive sputtering, and in situ surface assessment of sputtering target. And then I will discuss some applications of sputtering. So in the old days, we can see that we can, actually in more of the cases, we deal with both materials, but for certain applications, we can modify, we can tailor the surface properties as per our requirements. If you see the Porta Rosa Road of the 14th century in Italy, maybe you can change the surface properties to get your result. But when we talk about the surface kind of coatings, it must be very specific to your use. For example, if we have the similar coating on the one region, but your working condition is different, you have to deal with maybe the different environmental conditions, the different temperature. The same surface is not enough. Similarly, you have the good kind of surface coatings on the metal, but it's exposed to the different humid conditions. You have to reconsider, you need different type of coating. So we have the lot of coating, we have the different type of coating, but we have to select the right coating for your applications. If you see the history of the coatings, because we can use the coating for different applications like corrosion, appearance, frictions, and we can do the non-metals, we can simply change the appearance. We have the anti-reflection. So there are so many parameters that we can change by tailoring the surface of the materials. I will not go into the detail. If we have the product, we can add the value of the product. For example, we have the crankshaft. When we have some plasma nitriding, so that we have the same bulk material, but of course we have increased the life of the component. So the surface technology basically enhance the capacity or the efficiency of the products. So let's define what are the coatings. We have the bulk materials up to certain thickness, like up to 1 millimeter. I can say we have the plate, we have the sheet, we have the foil, thick film, and we will talk about the thin films. When the thickness is less than 5 micrometer, we call it like the thin films. There are so many types of the depositions. We have the chemical depositions, the vapor reacts chemically. We have the physical depositions, the particle physically attached with the surfaces. In the physical vapor deposition, as Dr. Shahzad has already elaborated, that we first convert the materials into the vapor phase, and then that material is deposited on the substrate. The history of the PVD is it first started like 1850s by the group. They started DC discharge experiments, and until 1980, we first introduced the PVD titanium nitride coating for the industrial use. So let's see what's the relation between the vacuum and the PVD. Actually, if we want to define the vacuum, the better way is we define the mean free path. If we have atmospheric pressure, particles are very close to each other, and the mean free path, the distance they travel before the collision with other particles, this is close to the nanometer scale. But if we generate the vacuum, basically we are increasing the mean free path. And for the PVD, we need a certain mean free path so that the evaporated vapor reach the substrate without the collisions. So it's a very, basic thumb rule. So if you consider your mean free path in millimeter, it is always 5 times the pressure in Pascal. So let's take an example. If we have the PVD apparatus in which the distance of the substrate from the source is like 150 millimeter, if the pressure is at 10 to the power minus 4 millibar, there is a possibility that only 75% of the vapor will reach the substrate without the collision. But if you want to say that the maximum particle should reach there, the minimum pressure must be like 10 to the power minus 5 millibar. So if the distance between the source and the substrate is like 150 millimeter, the minimum pressure must be 10 to the power minus 5 millibar so that the maximum vapor reach the substrate without the collisions. So this is the one aspect of the vacuum, that you must have a clear transportation of the vapor to the substrate. But there's some other reason. I will show the one XPS result in the lab. We were trying to make like titanium nitride by sputtering. We have a 99.99% titanium. We used a very clean nitrogen, but when at the end, the vacuum was like in the 10 to the power minus 5 millibar. But finally, when we checked the results, that was terrible because we have more titanium oxide rather than the titanium. There is a lot of titanium oxide. So when you are dealing with some different type of the coating, the level of vacuum must be very good so that all other impurities generally say that if you are in the range of -6, still there is a lot of oxygen. So if you want to say that you make your coating, you are making titanium nitride. It's either by plasma, I like arc, or like the sputtering. But if the vacuum is not good, you cannot get the pure titanium nitride. You will see the same situation like titanium and the titanium oxide. So in all these PVD coatings, the role of vacuum is very important. Dimensions are very important. Basically, as already explained by the Dr. Shahzad, we have the different type of technique like the PVD. I will not talk about the thermal evaporation of electron beam arc laser. I will basically little bit talk about the sputtering. Very brief with the evaporation, we convert the materials from the gas or the liquid, solid to liquid phase to the gas vapors and deposit on the substrate. We have different ways. We can have the resistive heating by simple resistive heating. We can use the electron beam because the resistive heating has some limitations. Up to a certain high temperature you can achieve with the resistive heating, but if you wanna melt something whose temperature is like 18 or 900 degrees centigrade, the resistive heating is not enough. You can go to the electron beam. You can use you can use the material with even higher melting point by the electron beam evaporation. You can use the arc, as already explained. This is one of the techniques. You can use even the laser. But now I will talk about the sputtering. So what's the basic difference about the other evaporation, PVD and the sputtering? In most of the cases, when you heat the material, it's either by resistive heating, either by the arc, either by the laser. Basically, you generate a kind of clusters of the materials. And maybe in one of the photo, you see that we can see some bubbles. In certain cases, like lateral, you can manage, but it's not always easy. But when we talk about the sputtering, what we do, we hit the surface with an ion, it shifts the energy, and then finally, the materials is sputtered. But there is a less probability that there will be the clusters. There's the most possibility that there will be the molecules, there will be the atom. And at the same time, the sputtered vapors or the atoms have the high energy as compared to the other. We get more densified coatings, and we have the more control on the parameters. So let's say how we can manage the sputtering yield. You have a single, if you see the previous slide, if it depends upon the energy. If the energy of the ion is less, it's just adhesion, incorporation, energetic spikes, and the certain limit, it starts sputtering. And if you further increase the energy of the ions, it will be the ion implantation. So there is another issue. If the energy of ion is very high, like it's more than 10 kilo electron volt, again, there will be like thermal spike. So we don't need this region, because if there is a thermal spike, this is also kind of evaporation. So we control the energy of the ion in such a way that there is no thermal spike, and the ions transfer the energy to the molecules, and then atoms and the molecules are removed from the surface, and then they are deposited on the substrates. We have some advantages. We can deposit a variety of metals and alloys. Of course, in most of the cases, like even XPS, in situ cleaning, sputtering can be used for the in situ cleaning. And you have the more reproducible control by using these electrical parameters, because you are not heating. You are basically generating an ion, and you are using the voltage for their acceleration. And finally, the very big advantage of the sputtering, in most of the evaporation technique, you have a limitations to put your material for evaporation. Because if you have a board, you can place a certain amount of the material. If you want to coat a big substrate, or you want to use it for the longer time, you have the arrangement to replace different substrate. But using the sputter cathode, you can use a lot of material in one attempt. You don't have to flush your system and add the more materials to the crucibles or the boards or something like that. Now I will a little bit talk about the sputter yield. There are different parameters like the incident ion, angle of ion, energy, masses, and finally the binding energy of the target material. So if we strike the ions with the surface at the certain angles, we have good yield. In the other part of my presentation, I will explain that we actually developed the technique that we can in situ assess the surface profile of the sputtering target, because the surface profile, if the roughness of the sputtering target is changed during the sputtering process, the incident angles are changed and angular distribution, and even the sputter yield is changed. Of course, sputter energy, a different energy. If you see here, at the low energy, you have the less yield. You have a maximum yield at a certain region, and then there is no yield because you again shifted from this region to the thermal spike, and that there is no sputtering. We have another type of sputtering, that magnetron sputtering. We use the magnets to keep the electrons more closer to enhance the plasma density and to generate the more sputtering. We have two types of the sputtering setups. We have the planar magnetron, we have the cylindrical magnetron, and we have the rotating magnetrons. So what's wrong with some planar magnetrons? But in the planar magnetrons, when you have a static magnetic fields, a certain region is basically eroded less, and we got a kind of like race brakes on your source, the sputtering source. So in this way, you have the limitations. You can only use like the 40% of your source. And if after some time, if it is eroded at the very specific region, like the race brake, the rest is useless. But if we use the cylindrical magnetron sputtering, you see we have all this whole region. And here we have a very uniform sputtering. So we can utilize like the more material, like we can utilize like up to the 80% of your source. So how it looks inside, we have a magnet, we have the magnet assembly, and that is finally, and this rotates inside this one. So how So in sputtering, we also have a very good opportunity to add some gases to make some compounds. If we are sputtering titanium, we can add the nitrogen to make the titanium nitride. If we are sputtering aluminum, we can add oxygen to make the aluminum oxide. So we have a very good possibility to add nitrogen, oxygen, carbon dioxide, acetylene, and make like carbides, oxides, and nitrides. I will not go to the physics of this particular process. Actually, when we add a reactive gas, the compound that is formed by the gas and the material that is not formed on the substrate, but that is all formed on the target. So after a certain time, if you increase the pressure, let's see it here, if you increase the pressure of the nitrogen up to some extent, that will be utilized to make the nitride, but after that, there will be the more nitrogen because the nitrogen nitride will be also deposited on the your target, and finally your pressure will rise and you will be shifted to the poison region. In this terminology, we say that initially we are in the metallic region, but when there is a poisoning on the target, we are in the poisoning region. So here's our apparatus in the lab. So now I will very briefly talk about the techniques. As I mentioned that the incident angle is very important for the sputtering yield. And we found that after certain sputtering, the surface profile of the target is changed. We make an arrangement, or we can measure in situ the surface morphology of the target. So we, for this one, we use the laser beam outside the chamber. We believe that the surface is not uniform. It will be a combination of the tilted plane facets. And then by using a little mathematics, we can find that if we get the image of the laser scattered image or diffuse scattered image on the screen, we can somehow say that how the surface morphology of the target is. We get some images. we use an algorithms. And then finally, we also actually, before this one, we also measure the roughness by the mechanical profilometer to make sure that our data is correct. And finally, we see that we were able to see the surface profile, in situ surface profile of the sputtering target inside the chamber without removing the target or without disturbing the vacuum. Then we also use this technique to see how poison is the target. Because if you keep it running at different pressures of the reactive gas, your target is currently poisoned. We see that when the target is poisoned, the surface profile is also changed. So if we measure the surface profile and then we confirm that with different surface profile, there was a different layer or the thickness of the poisoning. And when you find the depoisoning time, we find that at the different surface morphologies, they have different thickness of the poisoning, and this depoisoning time confirm that our results are correct. So now I will very briefly show some applications of these sputtering techniques. Number one, we can coat a long area product, like we can coat a big gloss sheet, which is not possible like other evaporation techniques. Because in the evaporation, if you have the multiple sources, they are even not uniform. If we evaporate the material from the source, its evaporation curve is like cosine. It's not purely uniform. But if you have a long cylindrical sputtering target, you can coat big objects, large objects like the glass sheets. As you already know, that we can make very good compounds. We can make titanium nitride, we can make titanium aluminum nitride, and definitely with the coating of these compounds, we can enhance the life of these, the tools. There's a possibility if we want to coat a cylinder from the inside. So that was the one of the hurdle that we have to coat a cylinder by PVD the inside. So it's very difficult to use other evaporation techniques. But in case of these cylindrical magnetrons, you can make the arrangement because your target is sputtering like 360 degree. And if you make the arrangement to put your substrate in the cylindrical form, you can even coat them uniformly from the inside of the cylinder. If you are interested to coat the outside of the cylinder, you can do it easily. You can rotate it on any like evaporating techniques. But if you want to coat a cylinder from the inside, it was a bit difficult. One of the very good applications, if you want to coat different materials. So we succeeded to add the strips of different materials on the single source. And we programmed the actual rotation of that magnetron. So which material we want to coat? Our plasma is rotated automatically. It was programmed to that material. So if you want to coat initially titanium, the plasma is in front of titanium, you are coating the plasma. And then the next step is aluminum. And the next step can be the other material. So if you have some, although there are compounds, targets materials are available, but it's very easy to manage different materials with this technique. We can generate a very special techniques. Nowadays at the CERN, we are generating like non-evaporator getters. They have developed like if they coat titanium, zirconium, hafnium, vanadium, they can get a very low outgassing from the chamber because they are interested in very ultra high vacuum in the 10 power minus 10 millibar, and the outgassing is really a big problem. So by coating these very special materials like these compounds, they coated with the like magnetron sputtering, like titanium, zirconium, hafnium, and vanadium, they have successfully reduced the outgassing of the chambers. That's all. Thank you very much. Any question, please? Actually, it may happen, but in this case, in our setup, if you have a good cooling arrangement of your target, your magnet will not be disturbed. In our case, we have the water circulation inside the target. So in this case, we kept the temperature of the magnet to a certain level. If you have some arrangement, it's good. If not, definitely your magnet will be disturbed. So I have announcement. So now after closing of this session, we have a group photo. So please join us in the group photo. And secondly, today we have a dinner and a cultural show at another location. So the buses which will leave from here will come back to this location. So there's no issue of the transportation. Anybody who have already consented to go there can use the facility. Thank you. So with this is the end of the technical session, and tomorrow we will join again at 9. So please follow the time. Thank you very much.